Hey, welcome the night scientist of the universe. I'm so happy you're here with me today. Take a moment to settle in, maybe grab a warm cup of tea or coffee, and let yourself sink into your favorite chair. We're about to embark on one of the most remarkable journeys imaginable, one that spans billions of years and countless light years of space. This isn't just any story, it's the story of how something as magnificent as a galaxy comes to be. From the tiniest specks of cosmic dust to the breathtaking spiral arms that sweep across the darkness of space, like celestial brushstrokes painted by the universe itself. I want you to imagine that we're sitting together under a starlit sky, with the Milky Way stretching overhead like a river of light. Tonight, we're going to trace that river back to its very source, back to a time when there were no stars, no planets, no galaxies at all, just the infinite potential of what could be. This is a story of transformation, of patience, of the incredible forces that shape our cosmos, and most importantly, it's a story of home. Because every atom in your body, every breath you take, every thought you think, has its origins in the very processes we're about to explore together today. We are diving into the fascinating world of story of a galaxy, from dust to spiral arms. This is a tale that begins not with a whisper, but with the most spectacular event our universe has ever known. And it unfolds across eons of time in ways that will make you see the night sky with completely new eyes. We'll discover how the gentlest of cosmic breezes can sculpt entire star systems, how gravity becomes the artist of the cosmos, and how patience, infinite cosmic patience, transforms chaos into the most beautiful structures we can imagine. So let's begin this journey together, shall we? Let's travel back to the very beginning, to a time when everything that would ever be was compressed into a space smaller than the period at the end of this sentence. In the beginning, there was nothing. Not the kind of nothing you might imagine. When you close your eyes and see darkness, no, this was a nothing so complete, so absolute, that there was no space for darkness to exist, no time for silence to fill. It was a nothing that contained everything, and everything was about to become something extraordinary. Imagine, if you can, all the matter and energy that makes up every star you've ever seen, every planet, every grain of sand, every thought you've ever had, all compressed into a point so small that it makes the smallest thing you can imagine seem impossibly vast. And then, in an instant that defines all other instants, it happened. The Big Bang wasn't really a bang at all. There was no air to carry sound, no ears to hear it. It was more like the universe taking its first breath, exhaling space and time and possibility into existence. In that first fraction of a second, space itself began to stretch and expand, carrying with it the seeds of everything that would ever be. The temperature was so intense that it makes the core of our sun seem like a cool spring morning, and the forces at work were so powerful that they could reshape the very fabric of reality. Picture this moment like the opening of a flower, but instead of petals unfurling, it was space itself blossoming into existence. The universe was smaller than a marble, then smaller than a grape, then the size of a basketball, then a building, then a city, all in the tiniest fraction of a second. This wasn't just expansion, this was the birth of distance itself, the creation of the stage upon which all future cosmic dramas would unfold. The universe was creating room for itself to exist, writing the rules of physics as it went. In those first moments, the universe was so hot and dense that matter as we know it couldn't exist. There were no atoms, no molecules, just a sea of energy, so pure and intense that it would take hundreds of thousands of years for it to cool enough for the first atoms to form. Think of it like a cosmic soup, simmering at temperatures that would instantly vaporize anything we could imagine. The ingredients were all there: protons, neutrons, electrons, but they were moving so fast, and the energy was so intense that they couldn't come together to form the building blocks of matter. As the universe expanded, it began to cool, like a cup of tea left on a windowsill. But this cooling process was incredibly slow by our standards. It took about 380,000 years for the universe to cool enough for the first atoms to form. During this time, the universe was opaque, filled with a fog of charged particles that scattered light in all directions. It was like trying to see through a cloud that filled all of space. No stars could shine because starlight couldn't travel. Through this cosmic fog, then came one of the most important moments in cosmic history, the moment when atoms first formed. As the universe cooled below about 3,000 degrees Kelvin, electrons finally slowed down enough to be captured by protons, forming the first hydrogen atoms. This event, called recombination, was like the universe suddenly clearing its throat. The cosmic fog lifted, and for the first time, light could travel freely through space. The universe became transparent, and if there had been eyes to see, they would have witnessed the first cosmic dawn. But this dawn was strange and beautiful in ways that challenge our imagination. The universe was filled with a warm, orange glow, the afterglow of the Big Bang itself. This light, stretched and cooled by billions of years of cosmic expansion, still fills the universe today. We call it the cosmic microwave background, and it's like a baby picture of the universe, showing us how things looked when the cosmos was just a few 100,000 years old. The matter in the universe wasn't distributed evenly. There were tiny variations in density, like wrinkles in a sheet that had been slightly crumpled. These variations were incredibly small. We're talking about differences of just a few parts in 100,000. But these tiny fluctuations were the seeds of everything that would come later. They were the places where gravity would begin to work its patient magic, pulling matter together, grain by grain, atom by atom, over millions and millions of years. Imagine the universe at this time as a vast, dark ocean filled with hydrogen and helium gas, with tiny currents and eddies that were invisible to any observer but would shape the future of everything. There were no stars yet, no light except for the fading afterglow of creation. This was the dark age of the universe. Not dark because it was evil or empty, but dark because the lights hadn't been turned on yet. The universe was pregnant with possibility, waiting for the right conditions to give birth to the first stars. Gravity, that gentle but persistent force that makes apples fall and keeps our feet on the ground, began to work on these tiny density variations. Where there was slightly more matter, gravity pulled in more matter. Where there was slightly less matter, regions became even more empty. It's like how rich get richer and poor get poorer, but in the cosmic sense, dense regions became denser, empty regions became emptier. This process happened incredibly slowly, over millions of years. If you could have watched the universe during this time, it would have seemed perfectly still, like a photograph. But on timescales that dwarf human history, great changes were taking place. The tiny variations in density were growing, like seeds sprouting in the darkness. These growing concentrations of matter would eventually become the first galaxies, the first stars, the first planets, the first homes for complexity and beauty in the universe. The universe during this time was cold and dark, but not empty. It was filled with possibility, with the raw materials for everything that would ever be. Every atom of hydrogen and helium was a potential building block for future stars. Every tiny gravitational pull was a step toward the creation of the first cosmic structures. It was a time of incredible patience, when the universe was preparing the stage for the greatest show in existence, the formation of the first galaxies. As millions of years passed in the dark universe, something remarkable was happening in the regions where matter had begun to gather. Picture a vast, invisible web stretching across the cosmos, with nodes where matter was slowly accumulating. These weren't yet the bright, shining galaxies we see today, but rather dark, cold clouds of gas that were growing larger and denser with each passing millennium. The universe was like a patient sculptor, working with the finest tools imaginable, gravity, time, and the gentle dance of particles to create its first masterpieces in these growing concentrations of matter. The gas was mostly hydrogen and helium, the simplest elements in the universe. They drifted together so slowly that if you could have watched the process, it would have seemed like nothing was happening at all. But gravity is persistent, and over millions of years, these clouds grew larger and denser. As they did, something wonderful began to happen. They began to warm up. When you compress a gas, it heats up. It's the same principle that makes a bicycle pump warm when you're filling up your tires. As these cosmic clouds of gas contracted under their own gravity, they began to glow faintly with infrared light. They were becoming warmer, denser, and more active. Deep within these clouds, in the very centers where the gas was densest, temperatures were rising toward a critical threshold. Imagine one of these clouds stretching across distances that would take light thousands of years to cross. In its heart, gas was swirling and condensing, forming a knot of matter that was becoming hotter and denser with each passing year. The temperature climbed from a few degrees above absolute zero to hundreds of degrees, then thousands, then tens of thousands of degrees. The pressure mounted as more and more gas fell inward, drawn by the irresistible pull of gravity, and then, after perhaps 50 million years of this slow, patient accumulation, something magical happened. In the heart of one of these clouds, and then another, and then thousands more across the universe, the temperature and pressure reached a critical point. The hydrogen atoms that had been drifting peacefully through space for eons suddenly found themselves pressed together so tightly, moving so fast that they began to fuse together. Nuclear fusion had begun. This moment was like the universe striking its first match. In the center of these collapsing clouds, hydrogen nuclei were slamming into each other with such force that they stuck together, forming helium. And when they did, they released energy, tremendous amounts of energy. The first stars were being born, and with them, the first light that the universe had seen since the afterglow of the Big Bang began to fade. These first stars were not like our sun. They were massive beyond imagination. Some were 100 times more massive than our sun, others even larger. They burned with an intensity that would have made them visible from across the galaxy if there had been anyone there to see them. They were blue-white giants, consuming their hydrogen fuel at a prodigious rate, living fast and burning bright. In the cosmic darkness, the birth of these first stars was a moment of triumph for the universe. After hundreds of millions of years of darkness, light had returned. But this wasn't the gentle, warm light of the Big Bang's afterglow. This was fierce, brilliant starlight, powered by the same nuclear furnaces that light our sun today. These stars were beacons in the darkness, lighthouses in the cosmic ocean, announcing that the universe had entered a new phase of its existence. As these stars shone, they began to change the universe around them. their light heated the gas in their vicinity, causing it to expand and glow. They created the first H2 regions, vast bubbles of ionized hydrogen that glowed with the characteristic red light that we still see in star-forming regions today. The universe was beginning to light up, region by region, star by star, like a city coming to life as evening falls. But these first stars were doing something even more important than providing light. In their cores, the nuclear furnaces were not only converting hydrogen to helium, but creating heavier elements as well. The intense pressures and temperatures inside these stellar cores were forcing helium nuclei to fuse together, creating carbon, oxygen, nitrogen, and other elements that had never existed before in the universe. The first stars were cosmic alchemists, transforming the simple hydrogen and helium of the Big Bang into the complex elements that would one day make planets and life possible. These stellar giants lived furiously and died young. Because they were so massive, they burned through their fuel incredibly quickly. While our sun will shine for about 10 billion years, these first stars lived for only a few million years, a cosmic blink of an eye. But their deaths were as spectacular as their lives. When their nuclear fuel was exhausted, they collapsed under their own gravity and then exploded in supernovas that lit up the universe like cosmic fireworks. These explosions were events of unimaginable violence and beauty. In a few seconds, a single star would release more energy than our sun will produce in its entire lifetime. The explosion would be visible from billions of light years away, briefly outshining entire galaxies. But more importantly, these explosions scattered the heavy elements that had been forged in the stellar cores across vast regions of space. Carbon, oxygen, silicon, iron, all the elements that would be needed to build planets and life, were spread through the cosmos like seeds on fertile ground. The universe was transforming. What had been a simple mixture of hydrogen and helium was becoming enriched with heavier elements. The deaths of the first stars were seeding space with the materials needed for the next generation of stars. And for the first time in cosmic history, the possibility of planets. The universe was learning to create complexity, to build structures that were more than the sum of their parts. As the first stars died and new ones were born from the enriched gas clouds, something else was happening. The matter in the universe was beginning to organize itself on larger scales. The gravitational pull of the first stars and the matter around them was helping to shape the first galaxies. What had started as tiny variations in density were growing into vast structures, the cosmic web that we still see today. The universe was no longer dark and empty. It was becoming a place of light and complexity, where matter could organize itself into increasingly sophisticated structures. The first stars had not only lit up the cosmos, they had provided the raw materials for everything that would come. After, they were the ancestors of every star that would ever shine, every planet that would ever form, every life that would ever exist. In the wake of the first stellar explosions, the universe had become a very different place. The pristine simplicity of the early cosmos, with its pure hydrogen and helium, had given way to something far more complex and interesting. Scattered throughout space were the heavy elements forged in the hearts of the first stars: carbon, oxygen, nitrogen, silicon, iron, and dozens of others. These elements, created in the nuclear furnaces of stellar cores and dispersed by spectacular supernovas, were like cosmic seeds, waiting to grow into new and wonderful forms. Imagine the universe at this time as a vast garden that had just been planted. The soil space itself was now enriched with nutrients that hadn't existed before. These heavy elements, though still vastly outnumbered by hydrogen and helium, were enough to change everything. They allowed gas clouds to cool more efficiently. They provided the raw materials for solid particles, and they opened up entirely new possibilities for how matter could organize itself. The process of star formation was becoming more sophisticated. The new generation of stars that formed from this enriched gas were different from their predecessors. They were smaller, on average, and longer-lived. Some were giants, like the first stars, but others were medium-sized stars, like our Sun, and still others were small, red dwarf stars that could shine for trillions of years. The universe was learning to create stars of all sizes and types, each with its own personality and destiny. As these new stars formed, something unprecedented began to happen around some of them. The heavy elements in the gas clouds didn't just disappear into the stars. Some of them remained in the surrounding space, where they began to stick together in ways that pure hydrogen and helium never could. Tiny grains of dust began to form, particles so small that billions of them could fit on the head of a pin, but so important that they would change the course of cosmic evolution. These dust grains were like cosmic glue. They provided surfaces where atoms could meet and stick together, forming more complex molecules. In the cold regions of space, far from the heat of stars, these grains became coated with ice, frozen water, carbon dioxide, ammonia, and other simple compounds. They were the first solid objects in the universe, tiny specks of matter that floated through space like microscopic snowflakes. The presence of dust changed how gas clouds behaved. Pure hydrogen and helium gas has a hard time cooling down once it's been heated, but dust grains are excellent radiators of heat. They absorb energy from their surroundings and re-emit it as infrared radiation, cooling the gas clouds and allowing them to contract more efficiently. This meant that star formation could happen more easily and in more places than it had in the early universe. As millions of years passed, these dust grains began to play an even more important role in the disks of gas and dust that surrounded newly forming stars. The grains began to stick together. Static electricity, the same force that makes socks cling to your shirt when you take them out of the dryer, helped tiny particles attract each other. Dust grain stuck to dust grain, forming larger particles, then pebbles, then rocks, then boulders. This process of accretion was incredibly slow by human standards, but fast by cosmic ones. Over millions of years, the dust grains in these protoplanetary disks grew larger and larger. They formed a hierarchy of sizes, from microscopic grains to pebbles to rocks to asteroids. And in some cases, when conditions were just right, these growing objects became large enough that their own gravity began to help them sweep up more material. Picture one of these early solar systems with a young star at its center and a disk of gas and dust swirling around it. In this disk, countless tiny dramas were playing out. Dust grains were colliding and sticking together, forming larger and larger aggregates. Some collisions were gentle, allowing particles to stick together. Others were violent, shattering the participants back into smaller pieces. It was a process of trial and error, of construction and destruction, played out on a scale that spanned millions of kilometers. The temperature in these disks varied dramatically with distance from the central star. Close to the star, it was hot enough to vaporize most materials, leaving only the most refractory substances, metals and silicates, to condense into solid form. Further out, where it was cooler, water could freeze into ice, along with other volatile compounds. This temperature gradient created different zones in the disk, each with its own characteristic materials and its own potential for planet formation. In the inner regions of these disks, where only metals and silicates could condense, the first terrestrial planets began to form. These were worlds of rock and metal, dense and relatively small, like the Earth, Mars, Venus, and Mercury in our own solar system. The process was violent and chaotic, with countless collisions between planetesimals, the building blocks of planets. Each collision released enormous amounts of energy, heating the growing planets until they glowed red-hot. Further out, beyond what we now call the frost line, where water and other volatiles could freeze, a different kind of planet formation was taking place. Here, the solid materials available for planet building included not just rocks and metals, but also vast amounts of ice. This meant that much larger solid objects could form, and when they did, something remarkable happened. If a growing planet became massive enough, about 10 times the mass of Earth, it could begin to capture the hydrogen and helium gas directly from the surrounding disk. These gas giant planets grew to enormous sizes, hundreds of times more massive than Earth. They were like failed stars, massive balls of gas that never quite became hot enough to ignite nuclear fusion. But they were important players in the cosmic drama, shepherding smaller objects with their gravity, clearing out regions of their disks, and sometimes flinging asteroids and comets into the inner solar system. The formation of these first planetary systems was a messy, violent process. Planetesimals crashed into each other at tremendous speeds, sometimes sticking together to form larger objects, sometimes shattering into fragments. The young planets were bombarded by asteroids and comets, their surfaces scarred by countless impacts. The heat from these collisions kept the planets molten for millions of years, gradually cooling as the bombardment lessened. But even in this chaos, something beautiful was happening. The universe was learning to create complexity on a new scale. It had mastered the art of making stars, and now it was learning to make planets. These worlds were laboratories where new kinds of chemistry could take place, where the heavy elements created in stellar core could combine in ways that were impossible in the vacuum of space. On some of these worlds, particularly those at the right distance from their stars, not too hot, not too cold, liquid water could exist on the surface. This was a crucial development, because liquid water is an excellent solvent, a medium in which complex chemical reactions can take place. The stage was being set for the next great leap in cosmic evolution, the emergence of life itself. The universe had come a long way from the simple hydrogen and helium of the Big Bang. It had learned to make stars, to create heavy elements, to form dust grains and planets. Each step had opened up new possibilities, new ways for matter to organize itself into increasingly complex structures. The cosmos was becoming a place where interesting things could happen, where the future was full of unlimited potential as the first billion years of cosmic history unfolded. The universe was beginning to show signs of the grand architecture that we see today. The tiny variations in density that had been imprinted in the first moments after the Big Bang had grown into vast structures, filaments of dark matter that stretched across millions of light years, creating a cosmic web that connected distant regions of space. Along these filaments, matter was flowing like water through invisible rivers, gathering in pools and eddies that would become the first galaxies. The formation of these early galaxies was a gradual process, like watching a time-lapse video of a flower blooming. but stretched over hundreds of millions of years. Gas clouds that had been drifting through space began to fall into the gravitational wells created by concentrations of dark matter. As they fell, they gained speed and began to swirl, forming rotating disks and irregular clouds that glowed with the light of their first stars. These proto-galaxies were smaller and more chaotic than the mature galaxies we see today. They were constantly merging with each other, like droplets of water coming together on a windshield. When two of these early galaxies collided, the result was a spectacular burst of star formation as their gas clouds compressed and triggered the birth of millions of new stars. The universe was going through its most active phase of star formation, creating new suns at a rate that would never again be matched in cosmic history. Picture one of these early galactic collisions unfolding over millions of years. Two spiral-shaped collections of stars, gas, and dust would approach each other, their mutual gravity gradually distorting their shapes. As they drew closer, long streamers of stars would be pulled out like taffy, creating spectacular tidal tails that stretched across vast distances. The gas clouds within each galaxy would compress and heat up, igniting bursts of star formation that would light up the cosmos with brilliant blue and white light. The supermassive black holes at the centers of these galaxies, objects millions of times more massive than our Sun, would also begin to interact. As matter fell into these black holes, it would heat up to millions of degrees, creating brilliant jets of energy that could be seen from across the universe. These active galactic nuclei were like cosmic lighthouses, beacons that could outshine all the stars in their host galaxies combined within these growing galaxies. The process of star formation was becoming more organized. The random, chaotic star formation of the early universe was giving way to more structured patterns. Stars were beginning to form in clusters, in associations, in the spiral arms of rotating disks. The universe was learning to create beauty on a galactic scale, with graceful spiral patterns and elegant elliptical shapes that spoke to the fundamental forces at work in the cosmos. The stars themselves were also becoming more diverse. The first generation of stars had been almost entirely hydrogen and helium, but each successive generation was enriched with heavier elements created by their predecessors. This meant that newer stars could have planets, and those planets could have the complex chemistry necessary for life. The universe was becoming more fertile, more capable of supporting the kind of intricate processes that would one day lead to biology. As these galaxies grew and evolved, they began to interact with their environment in new ways. The energy from their stars and active galactic nuclei heated the gas in the spaces between galaxies, creating vast bubbles of hot, rarefied plasma. These bubbles expanded and merged, creating a complex web of hot and cold regions that influenced how new galaxies could form. The universe was becoming a connected system, where events in one region could affect conditions millions of light years away. The spiral galaxies that were forming during this epoch were particularly beautiful and complex. They had rotating disks of stars and gas, with elegant spiral arms that wound outward from central bulges. These spiral arms weren't solid structures, but rather density waves that propagated through the galactic disk, triggering star formation as they passed. It was like watching a cosmic pinwheel, with new stars lighting up in the spiral arms and then fading as they aged and the wave moved on. The formation of these spiral arms was a delicate process that required just the right conditions. The galaxy had to be rotating at the right speed, with the right amount of gas and dust, and it had to be relatively undisturbed by major collisions. When all these conditions were met, the result was a galaxy of breathtaking beauty, with sweeping arms that traced perfect logarithmic spirals across the cosmos. In the centers of these galaxies, something remarkable was happening. The super black holes that had formed from the collapse of the first stars were growing larger and more massive. They were fed by streams of gas and dust that spiraled inward, heating up and glowing brightly before disappearing beyond the event horizon. These active galactic nuclei were some of the most energetic objects in the universe, capable of outshining entire galaxies and influencing the formation of new stars. Across vast distances, the relationship between these central black holes and their host galaxies was complex and symbiotic. The black holes helped to regulate star formation by heating and dispersing gas clouds, while the galaxies provided the material that fed the black holes. It was a cosmic dance of creation and destruction, where each partner influenced the other, in ways that shaped the evolution of the entire system. As billions of years passed, the galaxies continued to grow and evolve. They captured smaller satellite galaxies, like the Milky Way capturing the Magellanic Clouds. They formed groups and clusters, bound together by gravity into ever larger structures. The universe was developing a hierarchy of organization, from individual stars, 2 planetary systems, 2 galaxies, 2 galaxy clusters, each level building upon the previous one. The gas within these galaxies was constantly being recycled. Stars would form from gas clouds, live their lives, and then return their material to space through stellar winds and supernova. This recycled material, enriched with heavy elements, created in stellar cores, would then be available for the next generation of stars. The universe was becoming more efficient at creating complexity, learning to reuse and recycle its materials in ever more sophisticated ways. By the time the universe was a few billion years old, it had developed most of the structures and processes that we see today. There were spiral galaxies and elliptical galaxies, galaxy clusters and superclusters, active galactic nuclei and quasars. The cosmic web of dark matter had become more pronounced, with galaxies strung along its filaments like pearls on an invisible necklace. The universe had found its rhythm, its own way of organizing matter and energy into increasingly complex and beautiful forms. This was the stage upon which our own galaxy, the Milky Way, would make its entrance. Born from the merger of smaller proto-galaxies, fed by streams of gas from the cosmic web, and shaped by billions of years of star formation and galactic evolution, the Milky Way would become a perfect example of how the universe creates beauty. From chaos, order from randomness, and complexity from simplicity. The cosmic dance had begun, and it would continue for billions of years to come, creating wonders that we are only just beginning to understand. As we continue our gentle journey through the cosmos, we find ourselves in a universe that has grown remarkably from its humble beginnings. The primordial hydrogen and helium that once filled all of space has begun to gather itself into magnificent clouds, like morning mist collecting in the valleys of an ancient landscape. These cosmic clouds, stretching across distances so vast that light itself takes thousands of years to cross them, are the nurseries where the very first stars will be born. Picture, if you will, a vast ocean of gas floating in the darkness of space. This isn't the thin, wispy gas we might imagine, but rather a dense, cool collection of atoms that have been slowly drifting together for millions of years. The temperature in these stellar nurseries is incredibly cold, just a few degrees above absolute zero, making them some of the most frigid places in the universe. Yet, within this cold embrace, something magical is beginning to stir. The secret to understanding these stellar nurseries lies in recognizing that they are not uniform clouds of gas. Instead, they are filled with gentle currents and eddies, regions, where the gas is slightly denser in some places and slightly thinner in others. These variations are like ripples on a pond, so subtle that they might seem insignificant. But they hold the key to everything that follows in our cosmic story as gravity works its patient magic. These slightly denser regions begin to attract more and more gas from their surroundings. It's a process that unfolds over millions of years, like watching a flower bloom in the slowest possible motion. The denser regions grow denser still, pulling in material from farther and farther away, while the surrounding areas become increasingly empty and sparse. Within these growing concentrations of gas, something remarkable begins to happen. As more and more material gathers in one place, the gravitational pull becomes stronger and stronger. The gas starts to move, flowing inward like water circling a drain. But this is a drain that spans light years and takes eons to complete its work. The movement is so slow that if you could somehow stand within one of these clouds, you would never notice the motion, yet it is inexorable and unstoppable. As the gas falls inward under its own gravity, it begins to heat up. This might seem counterintuitive at first, since we started with such cold gas, but it's a fundamental principle of the universe that when matter is compressed, it becomes warmer. Think of pumping air into a bicycle tire. The pump becomes warm as you compress the air inside. In our stellar nursery, the same principle applies, but on a scale that dwarfs anything we experience on Earth. The heating process is gradual but relentless. What started as gas just a few degrees above absolute zero begins to warm to tens of degrees, then hundreds, then thousands. As the temperature rises, the gas begins to glow with a faint light, first in infrared wavelengths invisible to our eyes, then gradually shifting toward visible light as it grows ever hotter. Deep within the heart of these contracting clouds, the pressure is building to extraordinary levels. The gas is being squeezed from all sides by the immense weight of the material. Above it, like being at the bottom of an ocean that is light years deep. The temperature at the center continues to climb, reaching tens of thousands of degrees, then hundreds of thousands, then millions. But our story doesn't end with a simple bowl of hot gas. Something much more profound is about to occur, something that will fundamentally change the nature of matter itself and set the stage for all the complexity that follows in our cosmic tale. For when the temperature at the center of these contracting clouds reaches about 10 million degrees, the very atoms themselves begin to behave in ways that were impossible before. In the heart of our stellar nursery, where the temperature has climbed to unimaginable heights, we encounter one of the most beautiful and fundamental processes in the universe. The hydrogen nuclei, which are simply single protons, are moving so fast in the intense heat that they begin to overcome the natural force that normally keeps them apart. It's like watching dancers who have been circling each other cautiously suddenly embrace in a moment of perfect harmony. This dance of the nuclei is called nuclear fusion, and it represents the moment when our stellar nursery truly becomes a star. The process begins when two protons, moving at incredible speeds due to the enormous temperature, collide with such force that they overcome their mutual repulsion and bind together. In this cosmic marriage, one of the protons transforms into a neutron, creating the nucleus of heavy hydrogen, or deuterium. The fusion process releases energy in the form of light and heat, like a gentle flame that has been kindled in the darkness. But this is no ordinary flame. It burns with the power of nuclear forces, releasing energy that will continue to flow for billions of years. The light from this nuclear fire begins to push outward from the center of the star, creating a pressure that balances the inward pull of gravity. As the fusion reactions continue, the deuterium nuclei can fuse with other protons to form helium-3, and eventually, two helium-3 nuclei can combine to create helium-4, releasing 2 protons back into the stellar mix. This elegant chain of reactions, known as the proton-proton chain, is the primary source of energy for stars like our Sun. It's a process of breathtaking efficiency, converting a tiny fraction of the star's mass into pure energy according to Einstein's famous equation E equals mc squared. The energy produced in the stellar core doesn't immediately escape into space. Instead, it begins a remarkable journey that can take thousands or even millions of years to complete. The photons of light created in the fusion reactions are absorbed and re-emitted countless times as they work their way outward through the dense, stellar material. Each interaction changes the photon's energy slightly, like a message being passed through a long chain of whispers. As the energy slowly migrates outward, it encounters different layers of the star, each with its own temperature and density. In the outer layers, the material is cool enough that the hydrogen atoms can hold on to their electrons, creating a partially opaque barrier that causes the star's surface to glow with a steady, warm light. The exact color and brightness of this light depends on the star's mass and temperature, creating the beautiful variety of stellar colors we see in our night sky. But the story of our first stars is different from the stars we see today. These primordial giants were born from gas clouds that contained only hydrogen and helium, with no heavier elements to speak of. This seemingly simple composition had profound consequences for how these stars formed and evolved. Without heavier elements to help cool the gas clouds efficiently, the first stars had to be much more massive than most stars we see today, perhaps 100 or even 1,000 times more massive than our Sun. These massive first stars burned with incredible intensity, their surfaces blazing at temperatures that made them shine with brilliant blue-white light. They were cosmic lighthouses, beacons of nuclear fire that illuminated the universe for the first time since the cosmic microwave background was released. The light from these stellar giants began to spread outward at the speed of light, gradually, pushing back the darkness that had enveloped the cosmos for hundreds of millions of years. The intense radiation from these first stars had a profound impact on their surroundings. The high-energy photons streaming from their surfaces began to ionize the hydrogen gas in the space around them, stripping electrons from atoms and creating expanding bubbles of ionized gas. These bubbles grew larger and larger as more stars ignited, eventually overlapping and merging to create vast regions of ionized space. This process, known as reionization, marked the end of the cosmic dark ages and the beginning of a new era in the universe's history. The neutral hydrogen that had filled space since the cosmic microwave background was released was gradually transformed back into ionized gas, making the universe transparent to certain wavelengths of light once again. It was like watching the dawn break after the longest night in cosmic history. Within the nuclear furnaces of these first massive stars, an extraordinary transformation was taking place. The fusion reactions that had begun with simple hydrogen were just the opening act in a cosmic drama that would fundamentally change the chemical composition of the universe. As these stellar giants continued to burn through their nuclear fuel, they began to forge new elements in their cores, like cosmic alchemists transmuting base materials into precious metals. The process of stellar nucleosynthesis is one of the most elegant and important phenomena in all of physics. As the star exhausts the hydrogen in its core, the nuclear fires begin to die down, and gravity starts to reassert its dominance. The core contracts and heats up even further, reaching temperatures high enough to fuse helium nuclei together. When 3 helium nuclei combine in a process called the triple alpha process, they form carbon, the first element, heavier than helium, to be created in stellar cores. This might seem like a simple progression, but the creation of carbon represents a remarkable coincidence that makes all of chemistry, and ultimately life itself, possible. The triple alpha process requires a very specific set of conditions and a fortuitous alignment of nuclear energy levels. If the properties of atomic nuclei were even slightly different, carbon could not be formed in stellar cores, and the universe would remain a sterile place filled only with hydrogen and helium. Once carbon is present in the stellar core, it opens up new pathways for nuclear fusion. Carbon nuclei can fuse with helium to create oxygen, and oxygen can fuse with helium to create neon. Each successive fusion reaction requires higher temperatures and pressures, driving the stellar core to contract further and burn even hotter. The star develops a layered structure, like a cosmic onion, with different fusion reactions occurring at different depths in the innermost core. The most advanced fusion reactions create the heaviest elements the star can produce. Moving outward, each successive layer burns a different fuel and produces different elements. The silicon-burning layer creates iron and nickel. The oxygen-burning layer produces silicon and sulfur. The carbon-burning layer creates neon and magnesium, and so on. This stellar architecture is a testament to the incredible precision with which nuclear physics operates under extreme conditions. The massive first stars burn through their nuclear fuel at a prodigious rate, consuming in just a few million years what smaller stars like our Sun will burn over billions of years. Their intense luminosity is both a blessing and a curse. It makes them visible across vast distances and allows them to ionize enormous volumes of space. But it also means they live fast and die young in cosmic terms. As these stellar giants progress through their nuclear burning phases, they begin to develop unstable cores filled with iron and other elements near iron in the periodic table. Iron is special among the elements because it represents the peak of nuclear binding energy. Fusion reactions that create elements lighter than iron release energy, while those that create elements heavier than iron require energy input. This means that once a star's core fills with iron, nuclear fusion can no longer provide the energy needed to support the star against gravitational collapse. The iron core grows larger and larger as the star continues to burn silicon in the surrounding shells. When the core reaches a critical mass, roughly 1.4 times the mass of our Sun, it can no longer support itself against gravity. What happens next unfolds in a matter of seconds, but it represents one of the most violent and energetic events in the universe, the death of a massive star in a catastrophic explosion called a supernova. The collapse of the iron core is so rapid that it defies ordinary comprehension. The core, which might be the size of Earth, shrinks to a diameter of just a few kilometers in less than a second. The density becomes so extreme that protons and electrons are crushed together to form neutrons, creating a ball of nuclear matter denser than an atomic nucleus. A teaspoon of this neutron star material would weigh as much as a mountain. The implosion of the core creates a shock wave that races outward through the star at thousands of kilometers per second. This shockwave carries with it all the elements that the star has created during its lifetime: carbon, oxygen, neon, silicon, iron, and dozens of others. But the violence of the explosion creates conditions even more extreme than those in the stellar core, allowing for the formation of elements heavier than iron through rapid neutron capture processes. In the space of seconds, the supernova explosion creates gold, platinum, uranium, and all the other heavy elements that cannot be forged in the normal course of stellar evolution. These elements are then blasted into space along with all the other stellar products, creating an expanding shell of hot gas, enriched with the chemical diversity that will make planets and life possible. The explosion of the first massive stars represents a pivotal moment in cosmic history, the moment when the universe first became chemically rich enough to support the formation of rocky planets and, eventually, life itself. The supernova shockwaves racing outward from these stellar explosions carry with them the precious cargo of heavy elements, distributing them throughout the surrounding space like cosmic gardeners spreading seeds across a vast field. These expanding shells of enriched gas, called supernova remnants, are among the most beautiful and dynamic structures in the universe. They glow with the light of heated gas, creating spectacular displays of color and form that can be seen across vast distances. The shock waves compress and heat the surrounding interstellar medium, creating conditions that trigger the formation of new stars in nearby gas clouds. The process of stellar death and rebirth creates a feedback loop that profoundly shapes the evolution of the universe. Each generation of stars is born from gas that has been enriched by the deaths of previous generations, making it possible for newer stars to form with higher concentrations of heavy elements. This progressive enrichment, known as chemical evolution, is one of the key factors that makes the universe we observe today so different from the universe of the first few 100 million years. As the supernova remnants expand and cool over thousands of years, they begin to merge with the surrounding interstellar medium, gradually dispersing their heavy elements throughout larger and larger volumes of space. The mixing process is complex and chaotic, driven by turbulence, magnetic fields, and the continued influence of stellar winds and supernova explosions from other stars. Yet over millions of years, this chaotic mixing produces a remarkable result: a relatively uniform distribution of heavy elements throughout the galaxy. The heavy elements released by supernova don't remain in gaseous form indefinitely. As the hot gas cools and expands, the conditions become favorable for the formation of tiny solid particles called dust grains. These microscopic specks of matter, composed of carbon, silicon, oxygen, and other heavy elements, play a crucial role in the cooling and chemistry of interstellar space. They provide surfaces where atoms can stick together to form molecules, and they absorb starlight and re-emit it as infrared radiation, helping to cool the gas clouds where new stars will form. The formation of dust grains marks another important milestone in the cosmic story. For the first time in the universe's history, solid matter exists in the form of tiny particles suspended in space. These dust grains are the ancestors of the rocky material that will eventually form planets, asteroids, and all the solid objects we see in the universe today. They are also the building blocks of the complex organic molecules that will eventually give rise to life. As successive generations of stars live and die, the abundance of heavy elements in the galaxy continues to increase. The second generation of stars, born from gas clouds that have been enriched by the first supernova, can form with lower masses than their predecessors. The presence of heavy elements makes it easier for gas clouds to cool and fragment, allowing for the formation of stars with masses similar to our Sun. These smaller stars burn their nuclear fuel more slowly and live much longer, giving them time to develop stable planetary systems. The relationship between stellar mass and lifetime is one of the most important factors in determining whether a star system can support life. The most massive stars, while they enrich the galaxy with heavy elements, burn out too quickly to allow for the slow chemical evolution necessary for life to develop. The smallest stars, while they can burn for trillions of years, are so dim that their habitable zones are very close to the star, making it difficult for planets to maintain stable climates. Stars with masses similar to our Sun represent a kind of cosmic sweet spot. They are massive enough to burn steadily for billions of years, providing a stable energy source for planetary systems, but not so massive that they exhaust their fuel too quickly. They also go through a phase of stellar evolution that creates strong stellar winds, which can help strip away the primordial atmospheres of close-in planets, allowing for the formation of terrestrial worlds with thin atmospheres, suitable for life. The chemical enrichment of the galaxy doesn't happen uniformly throughout space. The rate of star formation and stellar death varies from region to region, creating a complex pattern of chemical abundance that influences where and when different types of objects can form. The central regions of galaxies, where star formation rates are highest, become enriched with heavy elements more quickly than the outer regions. This creates a metallicity gradient that can be observed in galaxies throughout the universe. The distribution of heavy elements also depends on the dynamics of the galaxy itself. Stellar motions, gas flows, and the gravitational interactions between different components of the galaxy all play roles in determining how quickly heavy elements spread throughout the galactic disk. The result is a complex, evolving pattern of chemical enrichment that reflects the galaxy's history of star formation and stellar death. As the universe continues to evolve and mature, the stage is being set for one of the most magnificent and important developments in cosmic history: the formation of the first galaxies. The dark matter halos that began to form in the early universe have continued to grow and merge, creating ever larger structures that will eventually host the stellar cities we call galaxies. The process is gradual but inexorable, like watching a vast metropolis slowly take shape in the wilderness. The growth of dark matter halos is driven by the same gravitational forces that created the first stars, but on a much grander scale. These invisible scaffolds of dark matter, which outweigh the ordinary matter by a factor of about 5-to-1, create the gravitational wells that will trap and accumulate the gas needed for galaxy formation. The largest halos, containing hundreds of billions of times the mass of our Sun, become the sites where the most massive galaxies will eventually form. The process of galaxy formation is far more complex than the formation of individual stars. While stars form from the relatively simple collapse of gas clouds, galaxies must assemble themselves from multiple components: dark matter, gas, stars, and the complex feedback processes that govern their interactions. The result is a delicate balance between gravitational attraction, which tries to pull everything together, and various forms of energy injection, which try to push things apart. The first galaxies to form are quite different from the majestic, spiral and elliptical galaxies we see in the nearby universe today. These early galactic building blocks are small, irregular, and chaotic, more like stellar nurseries than the organized stellar cities that will come later. They contain the second and third generations of stars, formed from gas that has been enriched by the supernova of earlier stellar generations. The star formation rate in these early galaxies is intense and episodic, driven by the merger of smaller, dark matter halos and the accretion of fresh gas from the intergalactic medium. Each burst of star formation creates new supernova, which injects energy into the surrounding gas and can temporarily halt star formation by heating and ejecting the gas from the galaxy. This creates a complex cycle of star formation, feedback, and recovery that shapes the evolution of the galaxy over cosmic time. The chemical enrichment process that began with the first supernova continues to accelerate as galaxies form and evolve. The concentration of star formation within dark matter halos means that the products of stellar nucleosynthesis are more efficiently retained and recycled within the galaxy, leading to a more rapid buildup of heavy elements. This chemical evolution is not uniform throughout the galaxy. The central regions, where star formation is most intense, become enriched more quickly than the outer regions. As galaxies grow through mergers and accretion, they begin to develop the complex structures that characterize mature galaxies today. The collision and merger of smaller galaxies can trigger intense bursts of star formation, creating starburst galaxies that shine with the light of billions of newly formed stars. These dramatic events reshape the galaxies involved, mixing their stellar populations and altering their chemical compositions. The gas dynamics within forming galaxies are incredibly complex, involving multiple phases of matter at different temperatures and densities. The hot gas that fills the galaxy's halo must cool and condense before it can form stars. But this cooling process is regulated by feedback from supernova and stellar winds. The interplay between cooling and heating creates a complex ecology of gas phases, from hot tenuous plasma to cold dense molecular clouds. The formation of the first galaxies also marks the beginning of a new era in cosmic structure. Formation. The universe is beginning to develop the hierarchical structure that characterizes it today, with galaxies organized into groups and clusters, which in turn are connected by filaments of dark matter and gas. This cosmic web provides the framework for all future structure, formation, and creates the environment in which galaxies will continue to evolve. The early galaxies also play a crucial role in the continued reionization of the universe. Their intense star formation produces numerous hot, massive stars that emit large amounts of ultraviolet radiation. This radiation escapes from the galaxies and ionizes the hydrogen gas in the surrounding intergalactic medium, creating expanding bubbles of ionized gas around each galaxy. As these bubbles grow and merge, they complete the process of reionization that began with the first stars. The efficiency of this reionization process depends on the properties of the early galaxies and their ability to leak ionizing radiation into the intergalactic medium. Small, low-mass galaxies are particularly important for reionization because they are more numerous than large galaxies and may be more efficient at allowing radiation to escape. The study of these early galaxies and their role in reionization remains an active area of research in modern astrophysics. As we watch these first galaxies take shape in the early universe, we are witnessing the birth of the structures that will eventually become the stellar cities of today. The Milky Way, Andromeda, and all the other galaxies we see in our local universe trace their origins back to these early, chaotic assemblages of dark matter, gas, and stars. The story of galaxy formation is ultimately the story of how the universe organized itself into the complex, beautiful, and life-supporting structures we observe today in the vast theaters of space, where our first generation of stars had been. Burning for millions of years, something profound was about to happen. These massive stellar giants, these cosmic furnaces that had been so faithfully converting hydrogen into helium and creating the first whispers of heavier elements, were approaching the end of their magnificent lives. But in the cosmos, endings are never really endings, they're transformations, passages from one form of beauty to another. Imagine, if you will, a star 50 times more massive than our sun, burning with the intensity of 1,000,000 suns combined. Deep in its core, the nuclear furnace has been working tirelessly, fusing lighter elements into heavier ones in a cascade of creation that would make any alchemist weep with joy. Hydrogen became helium, helium became carbon, carbon became oxygen, oxygen became silicon, and silicon became iron. Each step in this cosmic recipe released tremendous energy, keeping the star inflated against its own crushing gravity. But iron, iron is special. Iron is the cosmic endpoint, the place where nuclear fusion can no longer provide energy. When a star tries to fuse iron, it actually absorbs energy instead of releasing it. It's like trying to climb a mountain that gets steeper with every step until suddenly you're trying to climb straight up an infinite cliff. The star's core, suddenly deprived of the energy that had been holding it up for millions of years, faces a crisis of cosmic proportions. What happens next unfolds in mere seconds, but the consequences ripple through the galaxy for billions of years. The iron core, no longer supported by nuclear fusion, collapses under its own weight. In less than a second, a core the size of Earth shrinks to just a few kilometers across. The matter becomes so dense that protons and electrons are crushed together to form neutrons, creating a ball of nuclear matter so dense that a teaspoon of it would weigh as much as a mountain on Earth. This collapse happens so quickly that it creates a shockwave that races outward through the star at thousands of kilometers per second. When this shockwave reaches the outer layers of the star, it blasts them into space with such violence that the explosion can be seen from billions of light years away. This is a supernova, one of the most spectacular events in the universe, and it marks not just the death of a star, but the birth of possibilities we can barely imagine. The energy released in this explosion is almost incomprehensible. In just a few seconds, a single supernova releases more energy than our sun will produce in its entire 10 billion year lifetime. The temperatures reach billions of degrees, hot, enough to forge elements that could never be created in the cores of even the most massive stars. Gold, silver, platinum, uranium, all the heavy elements that make our world so rich and complex are born in these moments of stellar death. But perhaps the most beautiful part of this cosmic drama is what happens to all the elements that the star spent its life creating. The carbon that was forged in its core, the oxygen that would one day fill the lungs of living beings, the silicon that would become the foundation of rocky planets, the iron that would flow through the veins of countless future creatures. Of these elements are blown out into space, carried on the shock wave of the supernova-like seeds, scattered by a cosmic wind. Picture these elements spreading through the galaxy like ripples in a pond. The supernova blast wave races outward at speeds of thousands of kilometers per second, carrying with it the star's legacy. As it travels, it heats and compresses the surrounding interstellar medium, creating huge bubbles of hot gas that can span hundreds of light years. These supernova remnants, as astronomers call them, are like cosmic nurseries, rich with the heavy elements needed to build the next generation of stars and planets. The first supernova in our galaxy's history must have been a lonely event, exploding into a cosmos that was still relatively empty and quiet. But as more and more massive stars reached the end of their lives, the galaxy began to sparkle with these stellar fireworks. Each explosion added its own unique signature to the cosmic mix, enriching the interstellar medium with elements that had never existed before. Now, you might wonder what happened to the cores of these exploded stars. In many cases, they became neutron stars, objects so dense and strange that they challenge our understanding of physics. These neutron stars spin incredibly fast, sometimes hundreds of times per second, and they have magnetic fields trillions of times stronger than Earth's. Some of them sweep beams of radiation across space like cosmic lighthouses, and we call these pulsars. But the most massive stars, those giants that were perhaps 100 times more massive than our Sun, met in even more dramatic fate. When their cores collapsed, not even the pressure of neutrons could stop the collapse. The core continued to shrink, becoming so dense that space and time themselves became warped beyond recognition. A black hole was born, a region of space where gravity is so strong that nothing, not even light, can escape. These first black holes were like seeds of darkness scattered throughout the galaxy. Invisible but profoundly influential, they would grow over time, feeding on gas and dust, and eventually, some of them would become the supermassive black holes that we now know lurk at the centers of most galaxies. But we're getting ahead of ourselves. That's a story for later in our cosmic tale. The important thing to understand is that with each supernova, the galaxy was becoming richer, more complex, more capable of supporting the intricate chemistry that life requires. The universe was learning how to make complexity from simplicity, how to build elaborate structures from basic ingredients. It was developing what we might call cosmic wisdom, the knowledge encoded in the laws of physics that allows simple hydrogen gas to eventually become stars, planets, and perhaps even conscious beings contemplating their own origins as these stellar explosions continued over millions of years. They began to shape the structure of the galaxy itself. The hot gas from supernova explosions created vast cavities in the interstellar medium, pushing and sculpting the gas clouds that would eventually form the next generation of stars. The galaxy was becoming more three-dimensional, more structured, with hot bubbles and cool clouds creating a complex ecosystem of stellar birth and death. The heavy elements scattered by these explosions didn't just float around randomly. They began to settle into the disk of the galaxy, where they would be incorporated into new stars and planetary systems. This was the beginning of what astronomers call chemical evolution, the gradual enrichment of the galaxy with the elements necessary for complexity and life. Each new generation of stars would be born from gas clouds that were a little bit richer in heavy elements than the previous generation. These second-generation stars would live their lives, fuse their own elements, and eventually, many of them would also explode as supernova, adding their own contributions to the cosmic mix. The galaxy was developing a memory, a chemical record of all the nuclear processes that had occurred within its boundaries. As our galaxy settled into its rhythms of stellar birth and death, something remarkable began to emerge: a cosmic recycling program that would put any earthly environmental initiative to shame. The universe, it seemed, was remarkably efficient at reusing its materials, ensuring that nothing was ever truly wasted, that every atom would have multiple chances to be part of something beautiful and meaningful. The interstellar medium, that thin soup of gas and dust that filled the spaces between stars, was no longer the pure hydrogen and helium mixture it had been in the beginning. It was now seasoned with the products of stellar nucleosynthesis: carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements that have been forged in stellar cores and scattered by supernova explosions. These elements didn't just float around aimlessly. They began to tell their own stories, to follow their own paths through the galaxy. Consider a carbon atom, born in the nuclear furnace of a massive star some 12 billion years ago. This atom began its existence as hydrogen, simple and pure. But through the alchemy of stellar fusion, it was transformed into carbon, an element with the remarkable ability to form complex molecules. When its parent star exploded, our carbon atom was blasted into space, where it drifted for millions of years in the cold emptiness between stars. But space, we're learning, is not really empty. It's filled with invisible currents and flows, magnetic fields that guide the motion of charged particles, and gravitational influences that slowly but inevitably draw matter together. Our carbon atom, along with countless others, was slowly drawn toward a region where the gas density was slightly higher than average, a place where the next generation of stars would be born. These stellar nurseries, as astronomers affectionately call them, were vast molecular clouds that could span hundreds of light. They were cold, just a few degrees above absolute zero, and incredibly tenuous, so thin that they made the best vacuum we can create on Earth seem dense by comparison. Yet within these clouds, remarkable chemistry was taking place. The heavy elements scattered by the first generation of stars were not just sitting idle in these clouds. They were combining with each other and with hydrogen to form molecules, simple ones at first, like water and carbon monoxide, but gradually more complex ones as well. These molecules could radiate away energy, helping the gas clouds to cool and contract, setting the stage for the next generation of star formation. The presence of these heavier elements also meant that the new stars would be different from their predecessors. They would be cooler, less massive on average, and longer lived. More importantly, they would be accompanied by something that the first generation of stars lacked: planetary systems, rich in rocky material that could potentially support complex chemistry and even life. Our carbon atom, let's imagine, found itself incorporated into one of these new molecular clouds. As the cloud slowly contracted under its own gravity, it began to heat up and spin faster, eventually fragmenting into thousands of smaller clumps that would each become a star. Our carbon atom ended up in a clump that was destined to become a star not too different from our own sooner. Yellow dwarf star that would burn steadily for billions of years. But not all the material in the cloud ended up in the star. Some of it remained in a swirling disk around the young star, and it was here that our carbon atom would play its next role in the cosmic story. In this protoplanetary disk, dust grains began to stick together, forming larger and larger clumps. These clumps collided and merged, gradually building up rocky bodies that would eventually become planets. The process of planet formation was like a cosmic construction project that took place over millions of years. Small dust grains, many of them containing our carbon atom and others like it, slowly accreted into pebbles. Pebbles combined to form boulders, boulders merged to create mountains, and mountains collided to build worlds. It was a violent process, with constant impacts and collisions. But out of this chaos emerged order planets with solid surfaces, atmospheres, and the potential for even greater complexity throughout the galaxy. This process was repeating itself countless times. Each new generation of stars was more likely to have planets, and each generation of planets was more likely to have the chemical ingredients necessary for interesting chemistry. The galaxy was becoming not just a collection of stars, but a vast network of worlds, each one a unique laboratory where the laws of physics and chemistry could explore new possibilities. The recycling program wasn't limited to individual atoms either. Entire planetary systems could be disrupted and rebuilt. Close encounters between stars could fling planets out of their orbits, sending them wandering through interstellar space. Some of these rogue planets might eventually be captured by other stars, beginning new chapters in their cosmic stories. Even more dramatically, some stars existed in binary or multiple star systems, where they could exchange material with their companions. In these cosmic dances, we could see stellar vampirism, one star stealing material from another, growing larger and more massive while its companion withered away. Sometimes this process would culminate in spectacular explosions as the vampire star accumulated too much material and underwent its own nova or supernova explosion. The galaxy was developing a complex ecology with flows of material and energy, connecting stars and planets across vast distances. Stellar wind streams of charged particles flowing away from stars carried material from one system to another. Supernova shock waves could trigger the formation of new stars in nearby molecular clouds, creating chains of stellar birth that propagated across the galaxy like slow-motion fireworks. Perhaps most remarkably, the galaxy was also developing structure. On larger scales, the random distribution of the first stars was giving way to a more organized arrangement. Gravity was pulling stars together into clusters and associations, creating the first hints of the spiral arms that would eventually become one of the galaxy's most beautiful and recognizable features. These early spiral structures were nothing like the grand, sweeping arms we see in galaxies today. They were more like tentative suggestions, temporary concentrations of stars and gas that formed and dissolved over tens of millions of years. But they were the beginning of something important: the emergence of galactic-scale order from what had started as cosmic chaos. The formation of these structures was driven by what astronomers called density waves ripples in the gravitational field of the galaxy that traveled around the galactic disk like waves on the surface of a pond. As these waves passed through different regions of the galaxy, they would compress the gas and dust, triggering new episodes of star formation and creating the bright star-forming regions that outlined the spiral arms. It's important to understand that these spiral arms weren't permanent features carved in stone. They were more like traffic jams on a cosmic highway temporary, concentrations of matter that moved around the galaxy at their own pace. Stars would move into and out of the spiral arms during their lifetimes, spending some of their time in the bright, active regions and some in the quieter spaces between the arms. This cosmic recycling program was incredibly efficient. Astronomers estimate that the average atom in our galaxy has been part of multiple generations of stars. The oxygen in the water we drink, the carbon in our bodies, the iron in our blood, all of these atoms have been on epic journeys through space and time, cycling through stars and planets, molecular clouds and interstellar space for billions of years before finally becoming part of us. The galaxy was learning, evolving, becoming more sophisticated with each passing eon. It was developing the chemical complexity and structural organization that would eventually make it a suitable home for the incredible diversity of phenomena we see today, from the simplest chemical reactions to the most complex biological processes. As our galaxy continued its cosmic evolution, one force above all others was orchestrating the grand choreography of stars, gas, and dust that would eventually create the magnificent spiral structure we recognize today. Gravity, that most fundamental and persistent of nature's forces, was working on scales both intimate and vast, shaping the destiny of our cosmic home with patient, inexorable precision. To understand how gravity sculpted our galaxy, we need to think of it not as a static force, but as a dynamic, ever-changing dance. Every star, every gas cloud, every particle of dark matter was both responding to gravitational influences and creating its own gravitational field. The galaxy was like a vast orchestra, with billions of musicians all playing their parts in a symphony that had been composing itself for billions of years. In the early days of our galaxy's formation, when it was still a roughly spherical collection of gas and the first generation of stars, gravity was working to pull everything together toward the center. But the galaxy was also rotating, and this rotation created a centrifugal force that opposed the inward pull of gravity. The balance between these forces determined the galaxy's eventual shape and structure. Think of it like a spinning ball of dough that you're stretching and kneading. The rotation causes the dough to flatten out, creating a disc-like shape. Similarly, our galaxy's rotation caused it to flatten into the characteristic disc shape that we see today. The stars and gas that had the most angular momentum, the ones that were spinning fastest around the galactic center, ended up in the outer regions of this disk, while material with less angular momentum settled closer to the center. But this wasn't a simple, uniform process. The galaxy was far too complex for that. Different regions had different amounts of matter, different rotation speeds, and different gravitational influences. Some areas became overdense, attracting even more material and becoming the seeds of spiral arms. Other regions became creating the darker lanes between the arms where fewer stars formed. The process of spiral arm formation is one of the most beautiful examples of self-organization in the universe. It begins with tiny irregularities in the density of the galactic disk regions, where there's just slightly more matter than average. These overdense regions exert a slightly stronger gravitational pull on their surroundings, attracting more matter and becoming even denser. Meanwhile, the underdense regions lose matter and become even more sparse. As the galaxy rotates, these density variations get stretched and twisted by the differential rotation of the galactic disk. The inner parts of the galaxy rotate faster than the outer parts, just like the inner lanes of a racetrack are shorter than the outer lanes. This differential rotation takes what might start as a simple spiral pattern and winds it tighter and tighter, creating the magnificent spiral arms that we see in mature galaxies. But here's where the story gets really interesting. If differential rotation was the only force at work, the spiral arms would wind themselves up so tightly that they would disappear within a few 100 million years. Yet we see spiral galaxies that are billions of years old, still displaying their beautiful spiral patterns. This was a puzzle that astronomers called the winding problem, and solving it required understanding gravity's role in creating what we call spiral density waves. Imagine the galaxy as a vast, slow-moving traffic jam. The spiral arms are like regions of heavy traffic that move around the galactic highway at their own speed, different from the speed of the individual cars or, in this case, stars. As stars orbit the galaxy, they move into and out of these traffic jams, spending some of their time in the dense, active spiral arms and some in the quieter regions. Between the arms, these density waves are sustained by the gravitational interactions between all the matter in the galaxy. They're like ripples in the gravitational field that propagate around the galactic disk, compressing gas and dust as they pass and triggering new episodes of star formation. The bright blue stars that outline the spiral arms are actually quite short-lived. They form, burn brightly for a few million years, and then explode as supernova, all within the time it takes the density wave to pass through their region of the galaxy. The spiral arms, then, are not permanent structures, but rather temporary concentrations of matter and star formation that move around the galaxy like waves on the ocean. They're constantly forming and dissolving, creating new patterns of beauty and complexity as they evolve. It's a bit like watching a cosmic kaleidoscope, where the same basic elements are constantly rearranging themselves into new and fascinating configurations. Gravity also plays a crucial role in maintaining the overall stability of the galaxy. The central black hole that lurks at the galaxy's heart, growing slowly over billions of years, provides a gravitational anchor that helps keep the entire structure from flying apart. The dark matter halo that surrounds the galaxy like an invisible cocoon provides additional gravitational scaffolding that holds everything together. But gravity doesn't just operate on the scale of the entire galaxy. It's also working on much smaller scales, binding stars together into clusters and associations, shepherding gas clouds as they collapse to form new stars, and orchestrating the intricate orbital dances of binary and multiple star systems. The level of the cosmic hierarchy is governed by gravity's patient, persistent influence. One of the most remarkable aspects of gravity's role in galactic evolution is how it enables the galaxy to maintain its chemical memory. The heavier elements created by stellar nucleosynthesis don't just spread randomly throughout the galaxy. They follow specific paths dictated by gravitational flows, settling preferentially in certain regions and creating gradients of chemical composition that tell the story of the galaxy's evolution. For example, the inner regions of the galaxy, where star formation has been most active for the longest time, tend to be richer in heavy elements than the outer regions. This creates what astronomers call a metallicity gradient, gradual change in chemical composition from the center to the edge of the galaxy. This gradient is like a cosmic fossil record, preserving information about billions of years of stellar evolution and chemical enrichment. Gravity also enables the galaxy to interact with its neighbors. Our galaxy is part of a small group of galaxies, called the Local Group, which includes the Andromeda Galaxy and about 50 smaller galaxies. These galaxies are all gravitationally bound to each other, and their mutual gravitational influences shape their individual evolutions in subtle but important ways. Sometimes, gravity's influence can be more dramatic. When two galaxies pass close to each other, their gravitational fields can distort their shapes, trigger bursts of star formation, and even cause them to merge into a single, larger galaxy. These galactic interactions are like cosmic collisions, in slow motion, playing out over hundreds of millions of years. The galaxy's rotation also creates some interesting gravitational effects. As the galaxy spins, it generates what physicists call frame dragging, a subtle twisting of space-time itself. This effect is incredibly weak, but it demonstrates how gravity and rotation work together to create the complex, dynamic environment that we call home. Perhaps most remarkably, gravity enables the galaxy to be more than just a collection of stars and gas. It creates the conditions necessary for complexity to emerge stable orbits where planets can form, long-lived stars that can support biological evolution, and the chemical enrichment that provides the raw materials for life. Without gravity's organizing influence, the universe would be a much simpler, less interesting place. As we continue our journey through the story of our galaxy, or see how gravity's patient work over billions of years has created the magnificent spiral structure that we call home. We'll explore how the interplay between gravity, rotation, and stellar evolution has shaped every aspect of our cosmic neighborhood, from the smallest dust grains to the largest structures in the observable universe. By now, our galaxy had spent billions of years learning how to be a galaxy. It had mastered the art of stellar birth and death, developed sophisticated recycling programs for its chemical elements, and begun to organize itself into the beautiful spiral structure that would become its signature. But the story of galactic architecture goes much deeper than the spiral arms that catch our eye. It's a story of how gravity, chemistry, and time worked together to create a cosmic ecosystem of breathtaking complexity and beauty. The galaxy's disk, that vast, flat expanse, where most of the star formation takes place, had become a marvel of cosmic engineering. It was thin only about 1,000 light-years thick compared to its 100,000 light-year diameter, but within that thin disk was contained an incredible diversity of environments. Near the center, where the gravitational field was strongest, and the star density highest, the pace of life was frenetic. Stars formed rapidly, lived brief but brilliant lives, and exploded as supernova, enriching the local environment with heavy elements at a rapid pace. Moving outward from the center, the character of the galaxy changed gradually but profoundly. The star formation rate decreased, the chemical composition became less enriched with heavy elements, and the overall pace of cosmic evolution slowed down. It was like traveling from a bustling city center to quiet suburbs, each region with its own character and rhythm of life. The spiral arms themselves were not uniform structures, but rather complex ecosystems with their own internal organization. Along the inner edge of each spiral arm, where the density wave was compressing the gas most strongly, we found the most active star-forming regions. These were the cosmic construction sites where massive, short-lived stars were being born at a furious pace. The intense radiation from these young, hot stars ionized the surrounding gas, creating the beautiful emission nebulae that painted the spiral arms in brilliant reds and blues. Behind the wavefront, in the interior of the spiral arms, we found a different environment. Here, the gas had been processed by previous generations of star formation. The most massive stars had already lived their brief lives and exploded as supernova, leaving behind neutron stars and black holes. The surviving stars were older, redder, and more settled in their ways. This was the galaxy's suburban region, where the pace of life was more measured and the environment more stable. Between the spiral arms lay vast stretches of what astronomers call the interarm regions. These weren't empty spaces, but rather the cosmic equivalent of rural areas, sparsely populated regions where star formation proceeded at a leisurely pace. The gas here was thinner, the gravitational disturbances less frequent, and the overall environment more peaceful. It was in these quiet regions that some of the galaxy's most interesting chemistry took place, as complex molecules had time to form and evolve, without being disrupted by the violent events that characterized the star regions. The galaxy had also developed a complex vertical structure. The thin disk, where most of the star formation occurred, was surrounded by a thicker disk of older stars, and this, in turn, was embedded in a roughly spherical halo of ancient stars and mysterious dark matter. Each of these components had its own history and its own role to play in the galaxy's evolution. The halo stars were the galaxy's senior citizens, formed in the earliest epochs of galactic evolution when the galaxy was still a chaotic, turbulent place. These stars had witnessed the galaxy's transformation from a collection of gas clouds to the organized structure we see today. They were poor in heavy elements, having formed before the galaxy had time to enrich itself through stellar nucleosynthesis. But they were also incredibly long-lived, providing a stable gravitational backbone that helped hold the galaxy together. The thick disk was populated by stars of intermediate age, formed during the galaxy's middle years, when it was settling into its current structure. These stars showed more chemical enrichment than the halo stars, but less than the youngest stars in the thin disk. They were like the galaxy's middle-aged population, having lived through significant changes in the galactic environment, while still being young enough to participate in the galaxy's ongoing evolution. At the very center of the galaxy, hidden behind clouds of dust and gas, lurked one of the universe's most mysterious objects, supermassive black hole containing the mass of millions of suns. This central black hole wasn't just a passive inhabitant of the galaxy. It was an active player in galactic evolution, occasionally feeding on infalling gas and stars and releasing tremendous amounts of energy in the process. When the central black hole was actively feeding, it became what astronomers call an active galactic nucleus, spewing jets of high-energy particles thousands of light-years into space. These jets could trigger star formation in some regions while suppressing it in others, acting like a cosmic thermostat that regulated the galaxy's overall rate of stellar birth. The interstellar medium, the gas and dust that filled the spaces between stars, had also become incredibly sophisticated. It was no longer the simple mixture of hydrogen and helium that had filled the early universe. Instead, it was a complex, multi-phase medium with hot regions heated by stellar winds and supernova explosions, warm regions where star formation was beginning and cold, dense regions where complex chemistry was taking place. The dust grains floating in this medium were themselves marvels of cosmic engineering. They were tiny particles, smaller than the wavelength of visible light, but they played crucial roles in the galaxy's evolution. They absorbed starlight and re-radiated it at longer wavelengths, helping to cool the gas and making star formation possible. They also served as catalysts for chemical reactions, providing surfaces where atoms could meet and combine to form molecules. These dust grains were like tiny messengers, carrying information about stellar evolution throughout the galaxy. Each grain told a story. Some were made of carbon expelled from dying red giant stars. Others were composed of silicates formed in the atmospheres of massive stars. And still others were exotic materials forged in the hearts of supernova. Together, they created a cosmic library of information about the galaxy's chemical and evolutionary history. The magnetic fields that permeated the galaxy added another layer of complexity to its architecture. These fields, generated by the motion of charged particles in the galaxy's disk, created invisible highways that channeled the flow of cosmic rays and influenced the formation of stars. They were like the galaxy's nervous system, connecting distant regions and enabling them to communicate and influence each other across vast distances. The galaxy had also developed a complex relationship with its environment. It wasn't an isolated island of stars floating in empty space, but rather part of a larger cosmic ecosystem. It was surrounded by a halo of hot gas that extended far beyond the visible disk, and it was constantly exchanging material with this halo through processes that astronomers call galactic fountains and chimneys. Hot gas heated by stellar winds and supernova explosions would rise up out of the galactic disk, cool as it expanded into the halo, and then fall back down like cosmic rain. This process helped regulate the galaxy's star formation rate and distributed heavy elements throughout the galactic ecosystem. It was like a slow breathing process, with the galaxy inhaling and exhaling material over timescales of millions of years. The galaxy was also part of a larger structure called the local group, gravitationally bound to other galaxies, including the magnificent Andromeda galaxy. These galaxies were slowly orbiting around each other, their mutual gravitational influences subtly shaping their individual evolutions. In a few billion years, our galaxy and Andromeda would merge in a cosmic dance that would create an entirely new type of Galaxian elliptical galaxy that astronomers playfully call Milkomeda. But that merger was still far in the future. For now, our galaxy was in its prime, a mature spiral galaxy with a rich history and a bright future. It had learned how to maintain its spiral structure through multiple rotations, how to regulate its star formation rate to ensure a steady supply of new stars, and how to recycle its chemical elements efficiently. It had become a cosmic masterpiece, a testament to the power of simple physical laws to create structures of incredible beauty and complexity. As we pause to appreciate the architectural marvel that our galaxy had become, we can see how every component played a crucial role in the larger story. The spiral arms were not just beautiful patterns, but active regions where the galaxy's future was being forged. The interstellar medium was not just empty space, but a dynamic, chemical-rich environment where the raw materials for future generations of stars and planets were being prepared. The central black hole was not just a cosmic monster, but a regulator that helped maintain the galaxy's overall stability and evolution. Every star, every gas cloud, every dust grain was part of a larger symphony of cosmic evolution. The galaxy had become more than the sum of its parts. It had become a living, breathing ecosystem capable of supporting the incredible diversity of phenomena that make the universe such a fascinating place to explore and understand. In the gentle darkness of space, something extraordinary was happening that our eyes could never see. While the bright stars and glowing gas clouds captured all the attention, dancing their luminous waltz across the cosmic stage, a far more massive and mysterious partner was quietly leading the dance. This invisible partner was dark matter, and it was about to become the architect of everything we would eventually call a galaxy. Imagine, if you will, a vast spiderweb made of the finest silk, so delicate and transparent that it becomes invisible against the morning sky. Yet this web is strong enough to catch dewdrops, to support the weight of rainwater, and to provide structure for everything that comes to rest upon it. Dark matter behaves much like this invisible web, creating a framework throughout the universe that ordinary matter can cling to and build upon. In the early universe, when temperatures were still cooling from the ancient heat of creation, dark matter particles moved through space like gentle ghosts. They felt no electromagnetic forces, cast no shadows, and emitted no light. They were utterly invisible to any telescope that might have existed, yet they possessed something far more powerful than visibility: mass. And where there is mass, there is gravity, the most patient and persistent of all cosmic forces. As these dark matter particles drifted through the expanding universe, they began to feel the gentle tug of their own gravitational attraction. Like old friends finding each other in a crowded room, they slowly drew together, forming wispy clouds that grew denser and more substantial with each passing million years. These weren't the violent collapses we might imagine from Hollywood movies, but rather the most gentle and gradual of embraces, as patient as the tide and as inexorable as time itself. The dark matter didn't simply gather randomly throughout space. Instead, It followed the subtle density variations that had been printed into the fabric of the universe during its earliest moments. Think of it like water flowing down a hillside, naturally collecting in the low places and valleys. The dark matter flowed along these cosmic valleys, creating what astronomers would later call the cosmic web. A vast network of filaments and nodes that stretched across billions of light-years. At the intersections of these filaments, where multiple streams of dark matter converged, something remarkable began to happen. The gravitational pull became stronger, more concentrated, like the deep pools that form where mountain streams meet. These convergence points became the sites where the first dark matter halos would form, invisible cocoons that would eventually nurture the birth of galaxies. As these halos grew, they became like enormous, invisible bowls scattered throughout the universe. Each halo was a gravitational well, a depression in the fabric of space-time that could trap and hold other forms of matter. The halos themselves were patient, invisible, and utterly dark, but they were also incredibly powerful. A typical dark matter halo that would eventually host a galaxy like our own Milky Way contained about 1 trillion times the mass of our Sun, spread out over a region hundreds of thousands of light-years across. But here's where the story becomes truly beautiful. The dark matter halos weren't just random collections of invisible mass. They had structure, hierarchy, and purpose. Smaller halos formed first, like droplets of morning dew, and then gradually merged with their neighbors to create larger and larger structures. This process, called hierarchical structure formation, resembled nothing so much as a cosmic game of building blocks, where simple structures combined to create ever more complex and magnificent architectures. The dance of dark matter, halo formation, was choreographed by the fundamental forces of physics, but it unfolded with the grace and beauty of a natural process. Each halo that formed was unique, with its own mass, its own density profile, and its own gravitational personality. Some halos were compact and dense, destined to become the cores of massive elliptical galaxies. Others were more extended and gentle, perfect homes for the spiral galaxies that would eventually paint the universe with their graceful arms. As these invisible structures grew and evolved, they began to influence the ordinary matter around them, the hydrogen and helium gas that permeated the universe started to feel the gravitational pull of these dark matter halos. Like iron filings drawn to a magnet, the gas began to flow toward the halos, following the invisible highways carved by dark matter through the cosmos. This was the moment when the invisible scaffolding of dark matter began to reveal its purpose. The halos weren't just massive collections of mysterious particles. They were the foundations upon which all future galactic structures would be built. They were the invisible wombs that would nurture the birth of stars, the hidden frameworks that would support the spectacular architecture of spiral arms, and the patient guardians that would hold galaxies together for billions of years to come. The beauty of this process lay not just in its grand scale, but in its perfect timing. The dark matter halos formed at exactly the right moment in cosmic history, when the universe had expanded and cooled enough for complex structures to survive, but was still young enough for there to be plenty of raw material to work with. It was as if the universe had been waiting for this moment, when the invisible could finally begin to nurture the visible, when the dark could give birth to the light. Now that the invisible scaffolding of dark matter had been erected throughout the universe, it was time for the ordinary matter, the hydrogen and helium gas that would become the breath of future stars, to join the cosmic dance. This wasn't a violent conquest or a dramatic collision, but rather a gentle settling, like mist gathering in a valley at dawn. or clouds forming in the embrace of mountain peaks. The gas that filled the early universe was remarkably simple in composition, almost poetic in its purity. About 3/4 of it was hydrogen, the simplest and most abundant element in the universe, each atom consisting of just one proton and one electron dancing their eternal waltz. The remaining quarter was helium, only slightly more complex, with 2 protons, 2 neutrons, and 2 electrons in each atom. This was the legacy of the Big Bang nucleosynthesis, the ancient kitchen where the universe's first elements were cooked in the incredible heat of creation's first moments. As this primordial gas began to feel the gravitational pull of the dark matter halos, something beautiful and complex began to unfold. The gas didn't simply fall straight down into the halos like rain into a bucket. Instead, it began to spiral inward, following curved paths that were determined by the rotation of the halos themselves. You see, the dark matter halos weren't perfectly spherical or perfectly still. They had inherited tiny amounts of rotation from the quantum fluctuations of the early universe, and this rotation would shape everything that came after. Picture a figure skater beginning a spin. At first, they might rotate slowly with their arms outstretched, but as they pull their arms closer to their body, they spin faster and faster. The gas falling into the dark matter halos behaved in much the same way. As it spiraled inward, it spun faster and faster, and this rotation prevented it from simply falling straight to the center of the halo. Instead, it began to settle into a flattened disk, like cream settling on top of coffee or rings forming around a planet. But this wasn't just any disk. It was a disk with incredible potential. As the gas settled into this rotating configuration, it began to cool through a process that was both simple and miraculous. When gas particles collide with each other, they can emit photons, tiny packets of light that carry away energy. As these photons escaped into space, they took heat with them, and the gas gradually cooled down. It was like opening a window on a warm day, allowing the heat to escape and the room to become more comfortable. This cooling process was crucial, because cool gas behaves very differently from hot gas. Hot gas is energetic and turbulent, like water in a boiling pot, constantly moving and resisting compression. Cool gas, on the other hand, is more placid and cooperative, willing to be compressed and shaped by gravitational forces. As the gas in these early protogalactic disks cooled, it became denser and more organized, setting the stage for the next chapter in our cosmic story, the dance between gravity and gas. Pressure created a delicate balance that would determine the fate of these forming structures. Gravity wanted to pull everything together, to compress and concentrate the gas into ever denser configurations. Gas pressure, on the other hand, wanted to push outward, to expand and dilute the gas back into the surrounding space. The interplay between these two forces created regions of stability and instability, dense clumps and sparse voids that would eventually become the birthplaces of the first stars in these proto-galaxies. As the gas continued to cool and settle, it began to develop structure on smaller and smaller scales. What started as a relatively smooth disk began to develop spiral density waves, regions where the gas was compressed and other regions where it was stretched thin. These waves moved through the disk like ripples on a pond, but they were permanent, features maintained by the gravitational forces and the rotation of the system. They were the earliest ancestors of the spiral arms that would eventually make galaxies like our own. Milky Way, so breathtakingly beautiful, the cooling gas also began to fragment into smaller clouds, each one a potential stellar nursery. These clouds were held together by their own gravity, but they were also influenced by the larger scale motions of the galactic disk. Some clouds were compressed as they passed through the spiral density waves, making them more likely to collapse and form stars. Others were stretched and dispersed, their star-forming potential postponed for a later epoch. What made this process so remarkable was its self-regulating nature. As the gas cooled and became denser, it became more efficient at cooling, which made it denser still. But there were limits to how far this process could go. When the gas became too dense, it began to heat up again due to gravitational compression, and eventually it would reach a point where it could no longer cool efficiently. This created a natural thermostat that prevented the gas from cooling catastrophically and maintained the delicate balance necessary for gradual structure formation. The timescales involved in this process were vast by human standards, but swift by cosmic ones. It took hundreds of millions of years for the gas to settle into these rotating disks, cool to the point where it could fragment and begin to form the first generation of stars within the protogalactic environment. Yet this represented a cosmic blink of an eye, a remarkably rapid transition from the smooth, featureless universe of the cosmic dark ages to the structured, star-forming galaxies that would soon illuminate the cosmos. As we witness this ancient dance of gas and gravity, we're seeing the universe learn how to create complexity from simplicity, how to build intricate structures from the most basic ingredients. The hydrogen and helium gas that filled these early protogalactic disks carried within it the potential for everything that would follow the birth of new stars, the creation of heavier elements, the formation of planetary systems, and ultimately, the development of the complex chemistry that would make life possible. The breath of creation was now flowing through the invisible scaffolding of dark matter, filling the cosmic architecture with the raw materials needed for the next great phase of galactic evolution. The stage was set, the players were in position, and the universe was ready to begin creating the magnificent, spiral structures that would define the cosmic landscape for billions of years to come. As the cooling gas settled into its rotating disks within the dark matter halos, something magical began to happen. The protogalaxies were starting to develop their first heartbeats, rhythmic pulses of star formation that would give them life and personality. These weren't the steady, predictable heartbeats of a mature galaxy, but rather the irregular, sometimes frantic pulses of a cosmic newborn learning how to breathe. The first stars to ignite within these protogalactic disks were different from the stars we see today. They formed from the primordial gas that contained only hydrogen and helium, lacking the heavier elements that make star formation easier in the modern universe. These population 3 stars, as astronomers call them, were massive giants, some containing hundreds of times more mass than our Sun. They blazed with brilliant blue-white light, burning through their nuclear fuel at a furious pace. But it was their brief, violent deaths that truly began to shape the character of these early galaxies. When these massive stars reached the end of their short lives, they didn't simply fade away like smaller stars. Instead, they exploded as supernova, cosmic fireworks that briefly outshone entire galaxies. These explosions were like massive cosmic sneezes, ejecting heavy elements into the surrounding gas and creating shock waves that rippled through the protogalactic disk. The shock waves from these early supernova had a profound effect on the structure of the forming galaxies. They compressed nearby gas clouds, triggering new episodes of star formation in a cosmic chain reaction. At the same time, they heated and dispersed other regions of gas, creating bubbles and cavities that gave the galaxy a foamy, irregular structure. It was as if the galaxy was learning to sculpt itself, using the explosive deaths of its first stars as both chisel and hammer dot. This feedback process between star formation and stellar death created a complex rhythm in the early galaxy. Periods of intense star formation would be followed by explosive stellar deaths, which would both trigger new star formation and disrupt existing star-forming regions. The galaxy would pulse with waves of stellar birth and death, each cycle adding new layers of complexity to its structure. The heavy elements created by these early supernovae began to mix with the primordial gas, creating a more complex chemical soup. Carbon, oxygen, silicon, iron, and dozens of other elements joined the hydrogen and helium, like spices being added to a cosmic recipe. This chemical enrichment had profound consequences for the next generation of stars. With heavier elements available, stars could form more easily and in a wider range of masses. The galaxy was learning to create not just massive giants, but also medium-sized stars like our Sun, and even small, long-lived red dwarfs. As the chemical composition of the gas evolved, so did the structure of the galaxy itself. The heavy elements could cool the gas more efficiently than pure hydrogen and helium, allowing it to compress further and form denser structures. Dust grains began to condense out of the gas, tiny solid particles that would eventually become the building blocks of planets. The galaxy was not just forming stars, it was creating the raw materials for entire solar systems. The rotation of the protogalactic disk began to organize these star-forming regions into loose spiral patterns. The density waves that had formed in the gas created preferred locations for star formation, and these regions began to trace out the first hints of spiral structure. It wasn't yet the elegant, well-defined spiral arms that we see in mature galaxies, but rather a more chaotic, irregular pattern that resembled the stirring of cream in coffee, or the swirling of paint on an artist's palette, the dark matter halo that surrounded and permeated the galaxy continued to play a crucial role in this process. Its gravitational field provided the stable foundation that allowed the galactic disk to maintain its structure despite the violent feedback from star formation and stellar death. Without the dark matter halo, the explosive energy from supernova would have dispersed the gas entirely, preventing the galaxy from forming at all. The dark matter was like a patient parent, holding the galaxy together during its tumultuous adolescence. As millions of years passed, the galaxy began to develop a more organized structure. The central regions, where the gas was densest and the gravitational forces strongest, became sites of intense star formation. These central regions began to bulge outward, creating the first hints of what would eventually become the galactic bulge. The outer regions, where the gas was more diffuse and the gravitational forces weaker, formed stars more slowly and slowly. The galaxy was also beginning to develop what astronomers call a metallicity gradient, a gradual change in the abundance of heavy elements from the center to the outer edges. The central regions, where star formation was most active, became enriched with heavy elements more quickly than the outer regions. This created a chemical landscape within the galaxy, with different regions having different compositions and different potentials for forming various types of stars and planetary systems. Magnetic fields began to thread through the galaxy, created by the motion of charged particles in the rotating disk. These magnetic fields would eventually play important roles in regulating star formation and channeling the flow of gas through the galaxy. They were like invisible rivers, guiding the movement of charged particles and creating structure on scales, both large and small. The first galactic heartbeats were irregular and chaotic, but they were also creative and transformative. Each pulse of star formation added new elements to the cosmic recipe. Each supernova explosion carved new structures in the galactic disk, and each generation of stars built upon the legacy of those that came before. The galaxy was learning, growing, and evolving, developing the complex structures and processes that would eventually create the magnificent spiral architecture we see in the universe today. These early proto-galaxies were like cosmic laboratories, experimenting with different combinations of gas dynamics, star formation, and stellar feedback. Some experiments succeeded, creating stable, long-lived galactic structures. Others failed, leading to the disruption and dispersal of the protogalactic material. But even the failures contributed to the learning process, as their disrupted material would eventually be recycled into new star-forming regions or incorporated into more successful galactic structures. As we observe this ancient process of galactic formation, we're witnessing the universe's first attempts at creating the complex, organized structures that would eventually become the cosmic cities we call galaxies. The first galactic heartbeats were the rhythm of creation itself, the pulse of a universe learning to transform simple hydrogen and helium into the rich tapestry of stars, planets, and ultimately life that we see around us today. As the proto-galaxies continued to evolve and mature, their rotation began to play an increasingly important role in shaping their final architecture. The gentle spinning motion that had been inherited from the early universe was now being amplified and organized by the ongoing process of galactic assembly. Like a potter's wheel shaping clay, the rotation of these early galaxies was sculpting their structure in ways that would determine their appearance for billions of years to come. The disk of gas and stars that had formed within each dark matter halo was not uniform in its rotation. Different parts of the disk spun at different rates, creating a complex pattern of motion known as differential rotation. The inner regions, where the gravitational forces were strongest, rotated faster than the outer regions. This differential rotation created a shearing motion throughout the disk, like the way honey spreads when you stir it with a spoon. This shearing motion had profound consequences for the structure of the galaxy. As regions of gas moved at different speeds, they began to stretch and compress in regular patterns. Areas where fast-moving gas caught up with slower-moving gas became compressed, while areas where fast-moving gas pulled away from gas became stretched and thinned. These compression and expansion zones moved through the galactic disk-like waves, creating the density patterns that would eventually become spiral arms. The mathematics of this process is beautiful in its elegance. The differential rotation creates what astronomers call spiral density waves, patterns of compression and rarefaction that spiral outward from the galactic center. These waves move through the disk at a different speed than the stars and gas themselves, much like the way a traffic jam can move backward along a highway even though the individual cars are moving forward. The density waves create temporary traffic jams in the galactic disk, where stars and gas pile up and become more concentrated. Where these density waves compress the gas, conditions become favorable for star formation. The increased density and pressure trigger the collapse of gas clouds, leading to the birth of new stars. These newly formed stars illuminate the density waves, making them visible as the bright spiral arms that we see in mature spiral galaxies. The stars don't stay in the spiral arms forever. They eventually move out of the density wave and continue their orbits around the galactic center. But new stars are constantly being born in the spiral arms, maintaining their bright appearance over long periods of time. The formation of spiral structure was not an instantaneous process, but rather a gradual emergence that took hundreds of millions of years. The early proto-galaxies had only the faintest hints of spiral structure, irregular and chaotic patterns that resembled more the swirling of cream in coffee than the elegant spirals we see in mature galaxies. But as the galaxy continued to evolve, these patterns became more organized and pronounced. The number and tightness of the spiral arms depended on the specific properties of each galaxy. Galaxies with more massive central bulges tended to develop fewer, more tightly wound spiral arms. Galaxies with smaller central bulges developed more numerous, more loosely wound spiral arms. The speed of rotation also played a role. Faster rotating galaxies developed different spiral patterns than slower rotating ones. As the spiral structure developed, it began to influence the overall evolution of the galaxy. The spiral arms became highways for the flow of gas throughout the galactic disk. Gas would flow along the spiral arms, being compressed and processed as it moved. Some gas would be converted into stars, while other gas would be heated and dispersed by stellar feedback. The spiral arms became like cosmic recycling centers, constantly processing and reprocessing the raw materials of star formation. The rotation of the galaxy also created a stable dynamical structure that could persist for billions of years. The gravitational forces created by the mass distribution in the galaxy, combined with the centrifugal forces created by rotation, established a state of equilibrium. Stars and gas could orbit the galactic center in stable paths, neither falling inward nor flying outward. This dynamical stability was crucial for the long-term survival of the galaxy as a coherent structure. The dark matter halo surrounding the galaxy played a crucial role in maintaining this stability. The dark matter provided most of the gravitational force holding the galaxy together, allowing it to rotate as a stable system. Without the dark matter halo, the visible matter alone would not have enough gravitational force to maintain the observed rotation speeds, and the galaxy would fly apart. The dark matter was like an invisible foundation, providing the structural support needed for the visible galaxy to maintain its elegant spiral architecture. As the galaxy matured, its rotation curve, the relationship between orbital speed and distance from the center, settled into a characteristic pattern. In the central regions, the rotation speed increased with distance, as expected for a solid body. But in the outer regions, the rotation speed remained roughly constant, a surprising result that provided some of the first evidence for the existence of dark matter. This flat rotation curve became a signature of mature spiral galaxies, a testament to the invisible scaffolding that holds them together. The architecture of rotation also influenced the formation of other galactic structures. The rotation of the galaxy helped to flatten the gas disk, creating the thin, pancake-like structure that we see in spiral galaxies. It also helped to maintain the separation between the galactic disk and the more spherical distribution of older stars in the galactic halo. The rotation was like a cosmic architect, organizing the various components of the galaxy into a coherent and beautiful structure. The magnetic fields that threaded through the galaxy were also organized by the rotation. The differential rotation of the galactic disk stretched and amplified the magnetic fields, creating the complex magnetic structure that we observe in modern spiral galaxies. These magnetic fields would eventually play important roles in regulating star formation and channeling the flow of gas throughout the galaxy. As we contemplate this ancient process of galactic architecture, we're seeing the universe learn to create some of its most beautiful and organized structures. The spiral galaxies that emerged from this process represent a perfect balance between order and chaos, between the organizing influence of rotation and gravity and the disruptive effects of star formation and stellar feedback. They are cosmic cathedrals, magnificent structures that combine beauty, complexity, and stability in ways that continue to inspire and amaze us billions of years later. The architecture of rotation was not just about creating beautiful spiral patterns, it was about creating sustainable, long-lived structures that could continue to form stars and evolve for billions of years. The rotation provided the framework for galactic evolution, the foundation upon which all future generations of stars and planets would be built. It was the cosmic blueprint that would guide the development of galaxies like our own Milky Way, creating the stable, organized environments where complex chemistry and eventually life could flourish. As our galaxy continued to mature and settle into its cosmic rhythm, something truly magical began to unfold. The disk that had formed from countless generations of stellar birth and death was about to reveal one of nature's most beautiful patterns, like ripples spreading across a still pond. Waves of density began to move through the galactic disk, creating the magnificent spiral arms that would become the galaxy's most distinctive feature. These spiral arms didn't form the way you might expect. They weren't permanent structures, like the branches of a tree, but rather like waves of traffic on a cosmic highway. Imagine standing on a bridge watching cars during rush hour. Sometimes the traffic flows smoothly, but other times it bunches up, creating waves of congestion that move along the road. The spiral arms work in much the same way, except instead of cars, we have stars, gas, and dust moving in elegant patterns around the galactic center. The spiral density wave theory, first proposed by astronomers Lin and Xu in the 1960s, explains how these beautiful patterns emerge and persist. As the galaxy rotates, different parts move at different speeds. The inner regions spin faster than the outer regions, much like how a figure skater spins faster when they pull their arms in close. This differential rotation creates shear forces that would normally destroy any permanent spiral structure within a few rotations. But nature had a more elegant solution. Instead of permanent spiral arms, the galaxy created moving waves of density that sweep around the disk like the arms of a cosmic pinwheel. These waves compress the gas and dust as they pass, triggering new star formation and creating the bright, luminous regions we see as spiral arms. The waves themselves are invisible, but their effects are spectacular, lighting up the galaxy with the brilliant blue glow of young, hot stars. Picture a gentle breeze moving across a field of wheat. The breeze itself is invisible, but you can see its path as it creates waves in the golden grain. The spiral density waves work similarly, creating visible patterns as they compress and rarefy the stellar material in their path. The waves move at about 10 to 20 kilometers per second, which sounds fast but is actually quite slow compared to the orbital speeds of stars, which can reach 200 kilometers per second or more. As these density waves sweep through the galactic disk, they encounter vast clouds of hydrogen, gas, and dust. The compression from the waves' passage causes these clouds to collapse under their own gravity, initiating the process of star formation. This is why spiral arms appear so bright and blue in photographs of galaxies. They're not just randomly bright regions, but active stellar nurseries where new stars are constantly being born. The process is beautifully self-sustaining. As the density wave compresses the gas and triggers star formation, the most massive of these new stars burn through their fuel quickly and explode as supernova. These explosions heat and disperse the surrounding gas, creating bubbles and cavities in the interstellar medium, but they also enrich the gas with heavy elements and can trigger additional star formation in nearby clouds through their shock waves. This cosmic dance creates a pattern that persists for billions of years. Even though the individual stars and gas clouds are constantly moving in and out of the spiral arms. A star might spend only a few million years in a spiral arm during its entire lifetime, but the spiral pattern itself remains, created anew by each generation of passing material. The number of spiral arms in a galaxy depends on various factors, including the galaxy's mass, rotation speed, and the presence of central structures like bars. Our own Milky Way has 4 major spiral arms, each named after the constellation in which we see them most prominently: the Perseus arm, the Sagittarius arm, the Centaurus arm, and the outer arm. Between these major arms are smaller structures called spurs and branches, including the Orion spur, where our own solar system resides. As we step back to appreciate the full architecture of our mature galaxy, we see a structure of breathtaking complexity and beauty. The spiral arms sweep outward from the central bulge in elegant logarithmic spirals, each arm maintaining its pitch angle as it winds around the galactic center. This mathematical precision isn't coincidental, but emerges naturally from the physics of rotating disks and density waves. The central bulge itself has become a majestic structure, home to billions of older, redder stars. These stars, formed in the galaxy's youth, have settled into stable orbits around the supermassive black hole at the galactic center. The bulge glows with a warm, golden light, quite different from the cool blue of the spiral arms. It's like the difference between a cozy fireplace and bright daylight, each beautiful in its own way. Surrounding everything is the vast halo of dark matter, invisible but essential. This ghostly structure extends far beyond the visible disk, creating a gravitational scaffolding that holds the entire galaxy together. Within this dark matter halo, globular clusters orbit like ancient cities, each containing hundreds of thousands of the galaxy's oldest stars. These clusters are relics from the galaxy's formation, pristine time capsules that preserve the memory of those early chaotic days. The disk itself has developed remarkable structure. In addition to the spiral arms, it has organized itself into distinct populations of stars. The thin disk, where most of the star formation occurs, contains the youngest stars and is rich in heavy elements. Above and below this, the thick disk holds older stars that formed when the galaxy was still settling into its current configuration. Each population tells part of the galaxy's story, like rings in a tree trunk recording the passage of time. The interstellar medium between the stars has become a complex tapestry of different phases of matter. Hot, ionized gas fills vast cavities, carved out by stellar winds and supernova explosions. This gas glows faintly in X-rays, invisible to our eyes but detectable by space telescopes. Cooler gas forms, wispy clouds and filaments, often revealed by the radio waves emitted by hydrogen atoms, and scattered throughout are the dark, dense molecular clouds where new stars are born. Some of these molecular clouds are truly enormous, containing enough material to form millions of stars. The largest, called giant molecular clouds, can span hundreds of light years and contain the mass of 1,000,000 suns. They're the galaxy's most active star-forming regions, nurseries where entire clusters of stars are born together. The famous Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is just one small part of such a cloud. The spiral arms serve as highways for this star formation, channeling gas and dust into these molecular clouds and compressing them to densities where gravity can take over. The process is remarkably efficient, converting about 1 solar mass of gas into stars every year throughout the galaxy. This might not sound like much, but over billions of years, it adds up to the hundreds of billions of stars we see today. Each new generation of stars is slightly more enriched in heavy elements than the last. The first stars were made almost entirely of hydrogen and helium, but today's stars contain trace amounts of carbon, oxygen, silicon, iron, and dozens of other elements. These heavy elements are crucial for the formation of planets and, ultimately, for the chemistry of life. In a very real sense, we are made of stardust, our bodies containing elements forged in the hearts of stars that died billions of years ago. The galaxy has also developed a complex magnetic field, generated by the motion of charged particles in the interstellar medium. This field threads through the spiral arms and helps regulate star formation by providing support against gravitational collapse. It also channels the flow of cosmic rays, high-energy particles accelerated by supernova shockwaves, creating a network of invisible highways throughout the galaxy. Our galaxy doesn't exist in isolation, but participates in a larger cosmic dance. With its neighbors, the local group, our small cluster of galaxies, is slowly being drawn toward the much larger Virgo cluster by its immense gravitational pull. This motion, called the local group's peculiar velocity, carries us through space. At about 600 kilometers per second relative to the cosmic microwave background radiation, this journey through space subjects our galaxy to subtle tidal forces from other galaxies and the large-scale structure of the universe. These forces are gentle but persistent, slowly warping the galaxy's outer regions and perhaps contributing to the formation of its spiral structure. The galaxy breathes with these cosmic rhythms, expanding and contracting slightly as it moves through regions of different density. Closer to home, our galaxy's gravitational influence extends to dozens of smaller companion galaxies. The large and small Magellanic Clouds are the most prominent of these, visible as fuzzy patches in the southern sky. These irregularly shaped galaxies orbit our galaxy like moons, their own star formation triggered by tidal forces from our galaxy's gravity. The Magellanic Stream, a ribbon of hydrogen gas stripped from these galaxies, traces their orbital path across the sky. These interactions add complexity to our galaxy's structure. The gravitational pull of the Magellanic Clouds may help maintain the spiral pattern, while the gas they contribute adds fuel for future star formation. In about 4 billion years, the large Magellanic Cloud will likely merge with our galaxy, adding its stars to our collection and perhaps triggering a burst of new star formation. But the most dramatic change in our galaxy's future will come from its collision with the Andromeda Galaxy, our nearest large neighbor, currently approaching at about 120 kilometers per second. Andromeda will collide with our galaxy in approximately 4.5 billion years. This won't be a catastrophic crash, but rather a slow, graceful merger that will unfold over billions of years. The collision will fundamentally reshape both galaxies, disrupting their spiral structures and eventually creating a single, larger, elliptical galaxy. Astronomers have playfully dubbed this future galaxy Milkomeda, a combination of Milky Way and Andromeda. The merger will trigger intense star formation as gas clouds collide and compress, creating a spectacular fireworks display that will be visible from great distances. Despite the dramatic name collision, individual stars are so far apart that actual stellar collisions will be extremely rare. Instead, the stars will be redistributed into new orbits, creating the more spherical structure typical of elliptical galaxies. Our Sun, if it still exists, will likely end up in a much more eccentric orbit, sometimes diving deep into the galactic center, and sometimes swinging far out into the halo. For now, though, our galaxy continues its steady rotation, completing one full turn every 225 million years. This is the galaxy's year, and in the 4.6 billion years since the Earth formed, our solar system has completed only about 20 galactic years. We're currently in the galactic equivalent of late spring, with the Sun positioned between two major spiral arms in a relatively quiet region called the local bubble. The local bubble is a cavity in the interstellar medium, carved out by supernova explosions over the past few million years. It's filled with hot, thin gas and provides a relatively clear view of distant stars and galaxies. This cosmic clearing has been our home for millions of years, protecting us from the denser, more turbulent regions of the spiral arms, while still allowing us to witness the galaxy's ongoing star formation throughout the galaxy. Star formation continues in beautiful, complex patterns. The spiral arms act like vast gardens, nurturing the growth of new stellar families in their gravitational embrace. Each star-forming region has its own character, shaped by the local conditions of temperature, density, and magnetic field strength. In the dense cores of molecular clouds, where temperatures drop to just a few degrees above absolute zero, gravity slowly wins its battle against gas pressure. These cores collapse over millions of years, gradually heating up as they shrink. When the core temperature reaches about 10 million degrees, nuclear fusion ignites, and a new star is born. The process is like watching a flower bloom in extreme slow motion, each stage beautiful in its own way. The most massive stars, those with more than about 8 times the mass of our Sun, burn through their fuel quickly and live fast, dramatic lives. They shine with brilliant blue light, illuminating the gas around them and carving out cavities with their powerful stellar winds. These cosmic beacons are visible from great distances, marking the spiral arms with their brilliant glow. When these massive stars reach the end of their lives, they explode as supernova, briefly outshining entire galaxies. These explosions are among the most energetic events in the universe, releasing more energy in a few seconds than our Sun will produce. In its entire 10 billion year lifetime, the shock waves from these explosions sweep through the interstellar medium, heating gas, accelerating particles, and triggering new episodes of star formation. The lighter elements produced by these stellar explosions enrich the interstellar medium, providing the raw materials for planets and, ultimately, life. Oxygen, carbon, silicon, and iron, all essential for rocky planets and biological processes, are forged in stellar cores and distributed by supernova explosions. Each new generation of stars incorporates these heavier elements, gradually enriching the galaxy's chemical composition. Lower-massed stars, like our Sun, live much longer lives and die more gently. After exhausting their nuclear fuel, they shed their outer layers in beautiful planetary nebulae, creating some of the most stunning objects in the night sky. These glowing shells of gas, illuminated by the hot white dwarf star at their center, add their own artistry to the galaxy's appearance. The galaxy's star formation rate has changed dramatically over time. In its youth, when gas was abundant and the galaxy was still settling into its current structure, star formation proceeded at a much higher rate. Today, the galaxy forms stars at a more sedate pace, having used up much of its pristine gas supply. But star formation continues, sustained by gas recycled from dying stars and occasional infusions from the intergalactic medium. The distribution of star formation also varies across the galaxy. The inner regions, where gas densities are higher and stellar encounters more frequent, tend to have higher star formation rates. The outer regions, where the galaxy gradually fades into the intergalactic medium, have lower densities and form stars more slowly. This creates a gradient in stellar populations, with the inner galaxy containing more young, metal-rich stars and the outer galaxy harboring older, more metal-poor populations. Some of the galaxy's most spectacular star-forming regions are found where spiral arms converge or where the galaxy's rotation creates compression zones. These regions, often called star formation complexes, can span hundreds of light-years and contain dozens of individual star clusters. The Cygnus X region, one of the most active star-forming regions in our galaxy, contains enough raw material to form more than 1 million stars. The process of star formation is remarkably inefficient, with only about 1% of the gas in a molecular cloud actually ending up in stars. The rest is dispersed by stellar winds, radiation pressure, and supernova explosions. This inefficiency is actually beneficial for the galaxy as a whole, ensuring that star formation proceeds at a sustainable rate and that gas remains available for future generations of stars. Our galaxy doesn't exist in isolation, but is part of a vast cosmic web that connects all galaxies in the universe. This web, made visible by the distribution of dark matter and traced by the paths of galaxies and galaxy clusters, resembles a three-dimensional spider web stretching across billions of light-years. The cosmic web formed from tiny density fluctuations in the early universe, amplified by billions of years of gravitational evolution. Dark matter, invisible but gravitationally powerful, formed the scaffolding of this web, creating filaments and walls that channel ordinary matter into nodes where galaxies form. Our galaxy sits at the intersection of several such filaments. Part of a local structure called a local sheet, gas flows along these cosmic filaments, feeding galaxies and sustaining their star formation. This cosmic plumbing system is invisible to optical telescopes, but can be detected through its effects on the cosmic microwave background radiation and by observing the absorption lines it creates in the spectra of distant quasars. The filaments are tenuous, with densities only a few times higher than the cosmic average, but they contain enough gas to fuel galaxy formation for billions of years. Our galaxy's position in this cosmic web influences its evolution in subtle ways. The gentle infall of gas from the surrounding filaments provides fuel for ongoing star formation, while the gravitational influence of nearby structures helps maintain the galaxy's structure and may contribute to the persistence of its spiral arms. The galaxy is like a cosmic intersection where matter from across the universe converges to create the beautiful structure we observe today. The cosmic web also shapes the galaxy's magnetic field, which extends far beyond the visible disk into The surrounding halo, this field, generated by the motion of charged particles in the galaxy's plasma, connects our galaxy to the larger universe and provides pathways for cosmic rays and other high-energy particles. The field lines thread through the spiral arms and may help regulate star formation by providing support against gravitational collapse. On the largest scales, our galaxy participates in the expansion of the universe itself. The space between galaxies is expanding, carrying distant galaxies away from us at speeds proportional to their distance. This expansion, driven by the mysterious dark energy that makes up about 70% of the universe, ensures that our galaxy's gravitational influence will gradually diminish over cosmic time. But within our local group of galaxies, gravity still dominates over cosmic expansion. The Andromeda Galaxy, despite the expanding universe, is actually moving toward us because the gravitational attraction between our galaxies is stronger than the expansion of space. This will change in the far future after the merger is complete, as the combined galaxy will be more isolated and subject to the full effects of cosmic expansion. The cosmic web also provides a framework for understanding the galaxies. Chemical evolution. Different regions of the web have different histories of star formation and chemical enrichment, creating a complex mosaic of compositions. Gas flowing into our galaxy from the surrounding web brings with it the chemical signatures of star formation. In other regions, contributing to the galaxy's ongoing chemical evolution. Understanding our galaxy's place in the cosmic web helps us appreciate both its uniqueness and its connection to the larger universe. We're not just observers of cosmic evolution, but active participants in it. Our galaxy's story intertwined with the grand narrative of cosmic structure formation that began with the Big Bang nearly 14 billion years ago. As we near the end of our journey through the story of our galaxy, it's important to recognize that this isn't really an ending at all. Our galaxy is a living, breathing entity, constantly changing and evolving. Every day, new stars are born while others die. Gas flows through the spiral arms, and the great wheel of the galaxy continues its stately rotation. The galaxy's heartbeat is measured in millions of years, far longer than human lifespans, but brief in cosmic terms. Each rotation brings changes as spiral density waves sweep through the disk, compressing gas and triggering new episodes of star formation. The galaxy breathes with these rhythms, expanding and contracting slightly as it responds to internal dynamics and external influences. Within this grand structure, countless smaller stories unfold. Binary star systems dance around each other in elegant gravitational ballets. Planet-forming disks around young stars gradually coalesce into new worlds. Some of these worlds may harbor life, adding their own chapters to the galaxy's story. The galaxy isn't just a collection of stars and gas, but a vast ecosystem capable of supporting complexity and perhaps consciousness. The interstellar medium itself is alive with activity. Shock waves from supernova explosions sweep through space, heating gas and accelerating particles to tremendous speeds. These cosmic rays, mostly protons and atomic nuclei, spiral along magnetic field lines and eventually reach Earth, where they create beautiful auroras when they interact with our planet's magnetic field. In this way, the galaxy's activity directly touches our world. The galaxy's magnetic field lines themselves are dynamic, constantly reconnecting and rearranging as the galaxy rotates and evolves. These magnetic reconnection events can accelerate particles and create brilliant flares of radio emission. The galaxy hums with electromagnetic activity across the entire spectrum. from low-frequency radio waves to high-energy gamma rays. At the galactic center, the supermassive black hole, Sagittarius A*, occasionally flares to life when it captures and consumes nearby matter. These feeding events, while rare, can briefly increase the black hole's luminosity by orders of magnitude, sending waves of radiation rippling outward through the galaxy. The black hole's gravitational influence shapes the orbits of nearby stars, creating a dynamic, ever-changing environment in the galactic nucleus. The galaxy's population of stars is constantly changing as well. Old stars reach the ends of their lives and return their material to the interstellar medium, while new stars form from the enriched gas. This stellar recycling ensures that the galaxy's chemical composition continues to evolve, with each generation of stars slightly more enriched in heavy elements than the last. The galaxy's dark matter halo, while invisible, is far from static. Computer simulations suggest that it's filled with substructure, streams of dark matter from disrupted smaller halos, and perhaps even dark matter hurricanes that periodically sweep through the galaxy. These invisible currents may influence the galaxy's evolution in ways we're only beginning to understand. Climate change on galactic scales occurs as the galaxy moves through different regions of the cosmic web. Periods of enhanced gas accretion can trigger bursts of star formation, while passages through regions of lower density may lead to quieter periods. The galaxy's environment is constantly changing, and it adapts to these changes over millions of years. The galaxy also serves as a laboratory for testing our understanding of physics on the largest scales. The behavior of dark matter, the nature of magnetic fields in low-density environments, and the physics of star formation in different conditions all provide insights into fundamental physical processes. Our galaxy is both our home and our laboratory, a place where we can study the universe in exquisite detail as we conclude this gentle journey through the story of our galaxy. It's worth reflecting on our own place in this magnificent cosmic narrative. We are not separate from this story, but integral participants in it. Every atom in our bodies was forged in the heart of a star, or in the cosmic furnace of the Big Bang. We are literally made of stardust. Our very existence, a testament to the galaxy's billions of years of stellar alchemy. Our solar system formed about 4.6 billion years ago from a collapsing molecular cloud enriched by countless previous generations of stars. The heavy elements that make up our planet, and ultimately our bodies, were created in stellar cores and distributed by supernova explosions. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the hearts of stars that died long before the sun was born. We orbit the galaxy at a distance of about 26,000 light-years from the center, in a relatively quiet region between the major spiral arms. This location, sometimes called the galactic habitable zone, may have been crucial for the development of life on Earth. We're far enough from the galactic center to avoid the disruptive effects of its intense radiation and frequent stellar encounters, but close enough to benefit from the heavy element enrichment that comes from stellar processing. Our position in the galaxy has also given us a unique perspective on the universe. From our vantage point, we can see the full sweep of the galaxy's disk edge-on, revealing the beautiful band of the Milky Way that stretches across our night sky. We can study other galaxies and see how they've evolved, giving us insights into our own galaxy's past and future. The galaxy has been our home for the entire history of life on Earth. As our planet has orbited the Sun, and our solar system has orbited the galactic center, countless species have evolved and gone extinct. The galaxy has witnessed the rise of life from simple organic molecules to complex multicellular organisms, and eventually to conscious beings capable of contemplating the cosmos itself. We are perhaps the galaxy's first attempt at the first collection of atoms organized in such a way as to be capable of understanding their own cosmic heritage. Through our telescopes and theories, our space probes and computer simulations, we are beginning to comprehend the galaxy's structure and evolution. We are the galaxy's way of knowing itself. Our understanding of the galaxy has grown tremendously. Over the past century, we've learned that it's much larger than early astronomers believed, that it's one of billions of galaxies in the universe, and that it's embedded in a vast cosmic web of dark matter and ordinary matter. We've discovered that it's actively forming new stars, that it harbors a supermassive black hole at its center, and that it will eventually merge with the Andromeda galaxy. But perhaps most remarkably, we've learned that we're not separate from the galaxy but part of it. We're made of the same elements as the stars, governed by the same physical laws, and participating in the same cosmic evolution. The galaxy's story is our story, and our story is part of the galaxy's larger narrative. As we look to the future, we can imagine humanity's descendants spreading throughout the galaxy, perhaps establishing colonies on other worlds and eventually becoming a truly galactic civilization. We might learn to harness the energy of stars, to navigate the cosmic web, and to understand the deepest mysteries of dark matter and dark energy. We might even learn to communicate with other conscious beings that the galaxy has nurtured into existence. But even if we never leave our home planet, we are still participants in the galaxy's ongoing story. Every breath we take cycles carbon through the biosphere, carbon that was forged in ancient stars. Every heartbeat pumps blood enriched with iron from stellar explosions. We are walking, breathing examples of the galaxy's creative power, temporary arrangements of stardust that have somehow achieved consciousness and wonder. The galaxy will continue to evolve long after human civilization has passed into history. New stars will form, old stars will die, and the great spiral arms will continue their stately dance around the galactic center. In about 5 billion years, the sun will exhaust its fuel and expand into a red giant, perhaps making Earth uninhabitable. But even this ending is part of the galaxy's story, as the sun's death will enrich the interstellar medium with the elements it has produced, providing raw materials for future generations of stars and planets. The collision with Andromeda will reshape the galaxy into something new, but it will still be home to billions of stars and perhaps countless worlds. The merger will trigger new episodes of star formation, creating new opportunities for planets and life. The galaxy's capacity for renewal and transformation seems endless in the very far future. Perhaps trillions of years from now, star formation will eventually cease as the galaxy exhausts its supply of gas. The stars will grow old and die, leaving behind white dwarfs, neutron stars, and black holes. Even these remnants will eventually fade or evaporate, leaving only the faintest whispers of the galaxy's former glory. But that ending is so far in the future as to be almost incomprehensible. For now, and for countless generations to come, the galaxy will continue to be a vibrant, dynamic place, filled with wonder and possibility. New stars will be born, new worlds will form, and perhaps new forms of life will emerge to contemplate the cosmos and marvel at their place in the grand story of the universe. As you step outside tonight and look up at the star-filled sky, remember that you're not just observing the galaxy from a distance. You're part of it, a brief but beautiful arrangement of stellar matter that has somehow achieved the remarkable ability to wonder about its own origins. The galaxy's story is your story, and your story, however brief, is part of the galaxy's magnificent, ongoing narrative. The spiral arms that sweep across the night sky are not just distant patterns of light, but part of the same cosmic structure that gave birth to our solar system and ultimately to us. The ancient light of distant stars carries with it the history of stellar evolution, the memory of countless generations of stars that lived and died to create the elements that make up our world. When you see the Milky Way stretching across a dark sky, you're looking at our galaxy from the inside, seeing the combined light of hundreds of billions of stars. You're witnessing the result of nearly 14 billion years of cosmic evolution. From the first stirrings of structure in the early universe to the mature, majestic spiral galaxy we call home. Thank you for staying with me through this peaceful journey into the story of a galaxy, from dust to spiral arms. I hope that sharing this cosmic story has brought you a sense of wonder and perhaps a deeper appreciation for our place in the universe. The galaxy that surrounds us is not just a collection of distant stars, but our extended home. The vast structure that has nurtured the development of complexity and consciousness over billions of years in our busy daily lives. It's easy to forget that we're passengers on a small planet orbiting an ordinary star in the outer reaches of a typical spiral galaxy. But occasionally, when we take the time to look up and really see the night sky, we can feel our connection to this larger story. We can sense that we're part of something much grander than ourselves. Participants in a cosmic drama that began with the Big Bang and will continue for billions of years to come. The galaxy's story is one of transformation and renewal, of simple beginnings leading to incredible complexity and beauty. From the first wisps of hydrogen gas to the magnificent spiral arms studded with billions of stars. From the violent explosions of supernova to the gentle formation of planetary systems. It's a story of continuous change and evolution, and it's a story that's still being written. Every moment, new stars are igniting in stellar nurseries. Planets are forming around young stars, and perhaps new forms of life are taking their first tentative steps on distant worlds. The galaxy continues to evolve, to surprise us, and to reveal new wonders to those who take the time to look and wonder. I encourage you to continue exploring this story, whether through books, documentaries, visits to planetariums, or simply by spending time under the night sky. The galaxy has so much more to teach us, so many more secrets to reveal. And as we learn more about our cosmic home, we gain a deeper appreciation for both the vastness of the universe and the precious rarity of our existence within it. May your own journey through life be filled with wonder at the cosmic story of which you are a part. May you find peace in knowing that you are made of stardust, that you carry within you the creative power of the universe itself. And may you always remember that in looking up at the stars, you are not just observing the galaxy from a distance, but participating in its ongoing story of beauty, complexity, and endless possibility. Sweet dreams, fellow star travelers. The galaxy watches over us all, spinning slowly through the cosmic night, carrying us on our journey through space and time. We are all children of the stars, brief but beautiful expressions of the galaxy's creative power, temporary arrangements of cosmic dust that have somehow learned to wonder about their own origins and destiny. Until we meet again under the starlit sky, keep looking up, keep wondering, and keep marveling at the incredible story of which you are a part. The galaxy's story is far from over, and your chapter in it, however brief, is precious and unique. Thank you for joining me on this gentle journey through the cosmos, and may the stars always guide your way.